Hello there, and welcome to Science for Sleep. Where curiosity gets cozy, the universe lowers its voice a little, and even the brightest objects in existence are invited to behave calmly for the evening. Tonight, we are drifting toward one of the most intense, distant, and strangely beautiful families of objects astronomers have ever found. They are called quasars, and if stars are the quiet lamps of the cosmos, quasars are more like entire cities of light wrapped around invisible engines shining from the centres of galaxies so far away that their glow began travelling toward us before Earth had grass, flowers, birds, or anyone around to wonder why the sky was dark. That is already a rather big thought to bring to bedtime, isn't it? Somewhere out there in the deep distance, a supermassive black hole is feeding. Not nibbling politely either. It is pulling in gas, dust, and anything unlucky enough to wander too close, while the material around it heats up until it shines more brightly than the galaxy that contains it. It sounds dramatic, and it is. But from here, from our small and comfortable corner of the Milky Way, that violence reaches us as a faint point of light, a tiny signal on a telescope image, a clue arriving after billions of years of travel. The universe does like to hide its loudest secrets inside the smallest looking dots. Before we begin, let me ask you something gentle. Where are you listening from tonight? Are you somewhere under a clear sky, where a few stars are visible above rooftops or trees? Or are you tucked beneath city lights, where the nearest thing to a quasar might be a very determined street lamp outside your window? And what time is it where you are right now? It is a fitting question, because quasars are not just objects in space, they are also objects in time. Many of the quasars we study are so distant that seeing them is a little like opening an old letter from the young universe. Their light has crossed expanding space for billions of years, carrying news from a time when galaxies were still growing, colliding, feeding, and changing much more fiercely than they usually do today. If you find this journey soothing, intriguing, or just a peaceful place to rest your thoughts for a while, I would be grateful if you gave the video a like and maybe subscribed. It helps this small, sleepy corner of science reach other curious minds who may also enjoy learning about impossibly powerful black holes in the calmest possible way. There is something quietly funny about that, really. We're taking objects that can outshine whole galaxies and inviting them into a soft bedtime voice, as if a quasar were a restless house guest and we were gently offering it a cup of tea. So settle in, let your shoulders drop, and allow the day to loosen its grip a little. Tonight, we're not rushing through the universe. We're going to move slowly, one idea at a time, toward the bright hearts of galaxies and the strange types of quasars astronomers have learned to recognize. Some quasars shout across space in radio waves. Some are quieter in radio light but still blaze in visible ultraviolet and X-ray light. Some show broad lines in their spectra, telling us that gas is racing around a black hole at tremendous speeds. Some are partly hidden behind dust. Some look redder, some bluer, some blast great winds outward, and some point their jets almost directly at Earth, which is about as subtle as the universe ever gets. A quasar begins with a black hole, but not the kind you might imagine drifting alone in darkness like a silent cosmic drain. The black holes that power quasars are enormous, supermassive objects with millions or even billions of times the mass of our Sun. They sit in the centres of galaxies the way a heavy stone might sit at the bottom of a pond, shaping the motions around it. Yet the black hole itself does not shine. That is important. A black hole is dark by nature, because within a certain boundary light cannot escape. The brilliance of a quasar comes from what happens just outside that darkness. Gas spirals inward. It rubs, compresses, heats, and glows. The closer it gets, the faster it moves, until the region around the black hole becomes one of the most efficient light-making machines in the known universe. Imagine water circling a drain, but replace the water with superheated gas, replace the sink with a galactic centre, and replace the quiet little swirl with matter moving at a significant fraction of the speed of light. That is still not perfect, because real accretion disks are much stranger than kitchen plumbing, but it gives us somewhere to begin. The disk around the black hole is not simply falling in all at once. It is orbiting, colliding with itself, losing energy, heating up, and sending radiation into space. The energy comes from gravity. As matter falls deeper into the black hole's gravitational grip, gravitational energy is converted into heat and light. A surprisingly large fraction of the matter's rest energy can emerge as radiation before the material disappears beyond the event horizon. It is as though the black hole has placed a toll booth at the edge of oblivion, and the payment is light. For early astronomers, quasars were confusing because they looked almost like stars. The word itself comes from quasi-stellar, meaning star-like. In telescope images they appeared as points, not wide fuzzy galaxies. But when scientists examined their light carefully, they found something puzzling. Their spectra, the rainbow fingerprints that reveal what an object is made of and how it is moving, did not match ordinary stars. The lines were shifted far toward the red, which meant these objects were not nearby stars at all. They were incredibly distant, and if they were that distant, then they had to be unbelievably luminous for us to see them. A little point of light on a photographic plate turned out to be a galactic core blazing across the observable universe. It was rather like mistaking a lighthouse on the horizon for a firefly, then realizing the lighthouse is billions of light years away and somehow still visible. That discovery changed the scale of the question. Quasars were not just bright, they were absurdly bright. Some release more energy than all the stars in a large galaxy combined, and yet the main region producing that light is small compared with the galaxy around it, sometimes no larger than our solar system, or only a little larger, depending on how you define the active region. This is part of what makes quasars so useful and so strange. They pack extreme power into a compact space. They can vary in brightness over days, weeks, or months, and that variation tells astronomers that the light must come from a region small enough for changes to happen quickly. A galaxy full of stars cannot brighten and fade as one neat object over a weekend. But gas near a black hole can. As we move through the different quasar types, it helps to remember that many of these categories are not separate species in the way dogs and cats are separate animals. They are often different appearances of a related cosmic engine, seen from different angles through different amounts of dust, with different jet strengths, gas motions, feeding rates, and environments. Astronomy is full of this problem. The universe gives us light, and we have to work backward. We cannot fly to a quasar with a clipboard and ask it whether it identifies as radio loud or broad line. We have to infer its nature from photons that have been stretched by cosmic expansion and filtered through vast distances. Scientists are very good at this, but the universe does not always label its boxes clearly. One quasar may look loud in radio waves because it launches a jet that blasts charged particles outward at nearly the speed of light. Another may lack such a strong jet and appear radio quiet, though quiet here is a very relative word, like calling a thunderstorm soft-spoken because it is not also playing drums. A broad-line quasar reveals gas moving extremely fast near the central black hole, spreading spectral lines into wide features. A narrow-line quasar may be partly hidden, or arranged so that our view of the fastest gas is blocked by surrounding dust and material. Red quasars can be reddened by dust or shaped by the stage of their galaxy's growth. Blue quasars may show us a clearer, less obscured view of the hot accretion disk. BAL quasars, short for broad absorption line quasars, show signs of powerful winds flowing outward, leaving dark bites in the spectrum where gas absorbs certain wavelengths. Blazars are the more intense cousins in this family, where a jet is aimed nearly along our line of sight, so its light is boosted and made violently variable. And among blazars, astronomers have historically spoken of optically violent variable quasars, which is a wonderfully dramatic phrase, as if the object were not merely bright but personally committed to being inconvenient for calm measurement. These names may sound technical at first, but each one is really a clue. Every quasar type tells us something about direction, dust, speed, magnetism, feeding, and cosmic history. It tells us whether we are seeing the central engine directly or through a veil. It tells us whether the black hole is launching a jet or mostly radiating from its disk. It tells us whether gas is orbiting close in, drifting farther out, or being hurled away in a wind that may shape the future of the host galaxy. Quasars are not just bright decorations in the early universe, they are part of the story of how galaxies grow and regulate themselves. A feeding black hole can heat surrounding gas, drive winds, launch jets, and influence whether nearby material forms new stars or is pushed away. The central monster may be tiny compared with a galaxy, but it can affect the galaxy's life in ways that are wildly out of proportion to its size. It is rather like discovering that the quiet-looking person at the back of the meeting has been controlling the thermostat, the lighting, and the entire budget. The reason quasars matter so much is that they were more common when the universe was younger. Look far enough into space, and you're also looking far enough back in time to see galaxies during their more active years. There were more collisions, more gas-rich systems, more growing black holes, more opportunities for galactic centers to flare into brilliance. This means quasars act like markers across cosmic history. They help astronomers study the early universe, the growth of supermassive black holes, the gas between galaxies, and even the expansion of space itself. Their light can pass through clouds of hydrogen on its way to us, and those clouds leave absorption marks that reveal what the universe was like along the path. In that sense, a quasar is not only a lighthouse, it is also a flashlight shining through cosmic fog, showing us the material between here and there. There is also something deeply humbling about their distances. When we say a quasar is billions of light years away, it can become just another large number, and large numbers have a habit of becoming slippery in the mind. So try this instead. The light from some quasars began its journey before the sun existed. It crossed space while our solar system formed from a disk of gas and dust. It travelled while Earth cooled, oceans gathered, continents shifted, life began, vanished, returned in new forms, and eventually developed eyes that could look upward. Then, after all that, a telescope on a small planet caught a few photons and turned them into data. We are not just observing an object, we are receiving an ancient event. The quasar may have changed completely by now. It may have dimmed. Its fuel may have run low. Its host galaxy may have merged with another. But its old light is still arriving, patient and unchanged, like a message that never knew how long it would take to be read. That is one of the gentle paradoxes of astronomy. The farther away something is, the younger we see it. A distant quasar can be an ancient object from our point of view, and a young object in the universe's own timeline. It is old light from a young cosmos. This can feel strange, but it is also one of the reasons quasars are so valuable. They let us study eras we cannot visit. We cannot rewind the universe, but light has been doing a kind of recording for us, carrying snapshots across the dark. Every quasar is a timestamp, a beacon, and a question. Of course, for all their usefulness, quasars are not gentle places. If you could hover near one, which you absolutely should not attempt, even with a very sturdy umbrella, you would find an environment ruled by extremes. Radiation would flood space. Gas would orbit at enormous speeds. Magnetic fields would twist and channel plasma. Jets, if present, could stretch far beyond the host galaxy, carrying energy into intergalactic space. The central black hole would not be sucking the whole galaxy in, a common misunderstanding, because black holes obey gravity like everything else. Stars at safe distances can orbit them for ages. The danger belongs to the material that comes too close, loses its stable orbit, and joins the glowing disk. The quasar is not a vacuum cleaner. It is more like a furnace built by gravity, fed by the slow disorder of galactic gas. A calm way to picture a quasar is to imagine a vast galaxy at night. Billions of stars are spread through it, each one shining in its own small neighbourhood. Then, in the centre, matter begins to fall toward the supermassive black hole. The disk brightens. Radiation streams outward. Clouds of gas respond. Some material is pushed into winds. In certain cases, jets erupt along the black hole's rotation axis, narrow and powerful, like beams from a lighthouse that has forgotten how to be modest. From some directions, observers see the disk clearly. From others, dust blocks part of the view. If the jet points sideways, it looks different than if it points nearly toward us. The same basic engine can wear many observational disguises. This is why a journey through quasar types is really a journey around the black hole, above it, beside it, through dusty curtains, along jets, and into the moving gas that writes its story in light. The word type may sound neat and tidy, but quasars are not always tidy. Real objects can sit between categories. A quasar can be radio loud and show broad lines. It can be reddened and windy. It can be distant, dusty, variable, and jet-driven all at once. Astronomers classify them because classification helps us learn, not because nature promised to arrange itself into clean drawers. Nature prefers messy cupboards. Science is the slow work of opening them carefully and trying not to be hit by falling saucepans. With quasars, those saucepans are supermassive black holes, relativistic jets, hot plasma, dust, winds, and spectra full of clues. Spectra will become important in this journey, so let us gently introduce them now. When astronomers spread quasar light into its wavelengths, they see patterns of emission and absorption lines. These lines come from atoms and ions in gas near the quasar or along the path to Earth. Hydrogen, carbon, magnesium, oxygen, and other elements leave fingerprints in the light. If gas is moving quickly, those fingerprints widen, shift, or become distorted. If gas is flowing outward between us and the bright source, it can absorb certain colours and create broad troughs. If dust lies in the way, the light can look redder, because dust scatters and absorbs shorter blue wavelengths more effectively. So, when we speak about broad-line quasars, narrow-line quasars, red quasars, blue quasars, or broad absorption line quasars, we are really speaking about how matter has marked the quasar's light before that light reached us. Radio waves give another part of the story. Some quasars are strong radio sources because jets contain charged particles spiraling through magnetic fields, producing synchrotron radiation. Radio telescopes can reveal lobes stretching far from the galaxy, sometimes on scales so large that the central quasar seems almost small by comparison. These structures show that a black hole's influence can extend far beyond the region where its gravity directly dominates. Energy launched from the centre can travel outward, inflate bubbles, disturb surrounding gas, and leave long-lasting signatures in the galaxy's environment. A radio-loud quasar is not just shining, it is sending machinery into space. In contrast, radio-quiet quasars remind us that a black hole can be tremendously powerful without producing a large radio jet. Their light may still dominate the host galaxy. Their accretion disks may still blaze. Their winds may still shape gas around them. The absence of a strong jet does not mean the engine is weak. It means the engine is expressing itself differently. This is a helpful idea beyond astronomy too. Not every powerful thing announces itself in the same way. Some roar in radio waves, some glow steadily in optical and ultraviolet light. Some hide behind dust until infrared telescopes reveal them. The universe has many speaking voices, and quasars use nearly all of them. As we continue, we will also meet the idea of viewing angle. This is one of the simplest explanations that unlocks many confusing quasar differences. Imagine looking at a lamp surrounded by a thick ring of smoke or cloth. From above, you might see the bulb directly. From the side, the ring blocks it. If the lamp also has a narrow flashlight beam pointing out from its top, then standing in the beam would make the lamp look far brighter and more variable than standing off to the side. In active galaxies, the details are far more complex, but the principle matters. What we see depends partly on where we are. A cosmic object does not change just because we move around it, but its appearance can. Since we cannot move around distant quasars, we study many of them from many natural angles and piece together the pattern. There is a softness hidden inside that scientific process. We are tiny observers, unable to visit, unable to touch, unable to pause the universe and turn an object gently under a lamp. Yet by collecting light, comparing patterns, and building careful models, we can infer the shape of places no human will ever reach. A quasar becomes understandable not because it is nearby, but because the universe is consistent. Atoms leave the same fingerprints across the cosmos. Gravity follows rules, light carries information, and patient minds can read that information even after it has crossed billions of years. Tonight's path will begin with the basic heart of the quasar, the active galactic nucleus, where the supermassive black hole and its accretion disk create the central blaze. From there we will move outward into jets, radiolight, spectral lines, dust, colours, beaming and winds. Each step will add one more layer, not in a rushed way, but in the slow satisfying manner of turning down the lights in a large observatory and letting your eyes adjust. At first you see only darkness, then a few stars appear, then the Milky Way begins to show. Then, if you wait long enough, the sky becomes full of structure you were missing a moment before. Quasars ask us to hold two opposite ideas at the same time. They are among the most energetic objects in the universe, and yet most of them reach us as faint points of light. They are powered by black holes, the darkest objects we know, and yet they can outshine galaxies. They are ancient signals, but they help us understand cosmic growth. They are dangerous in their own neighbourhoods, but useful from ours. They are simple in their core idea, matter falling toward a supermassive black hole, and complicated in every real detail that follows. So as you settle further into the quiet, picture the night sky not as empty, but as layered with old messages. Somewhere beyond the stars you can see, beyond nearby galaxies, beyond structures so large they make human distance feel almost imaginary. There are quasars shining from the deep past. Some are launching jets, some are wrapped in dust, some are blowing winds into their galaxies, some are flashing and changing because their beams are aimed nearly toward us. Some are blue, some red, some loud, some quiet. Though even the quiet ones are only quiet by the standards of cosmic monsters, each one is a bright clue around a dark centre. The easiest way to begin understanding a quasar is not to imagine something exotic at first, but to imagine a galaxy. A real galaxy, with stars, gas, dust, star-forming clouds, old stellar neighbourhoods, young, bright clusters, wandering planets, and long, quiet spaces between everything. It may look peaceful from a distance, like a soft island of light, but at its centre, hidden inside that island, there may be a supermassive black hole. Not a small black hole left behind by one dead star, but a giant one with millions or billions of times the mass of the sun gathered into a region so compact and strange that ordinary language starts to run out of useful furniture. Most large galaxies seem to have these central black holes. Our Milky Way has one too, called Sagittarius A star, sitting about 26,000 light-years away in the direction of the constellation Sagittarius. It is massive, yes, but at the moment it is not behaving like a quasar. It is comparatively quiet. That does not mean it is harmless in the immediate neighbourhood, and it certainly does not mean you would want to park a spacecraft beside it and have a sandwich. But compared with a quasar, Sagittarius A star is like a sleepy fireplace with only a few embers glowing, while a quasar is more like the same fireplace suddenly being fed an entire forest. The difference is not simply the black hole itself. The difference is what the black hole is being given. A black hole does not shine by itself. That is one of the first things to keep gently in mind. The dark centre is dark because past the event horizon, light cannot escape. If there were nothing around it, no gas, no dust, no stars being disturbed, no material losing its way, it would be nearly invisible except for its gravity. A quasar is not the black hole glowing. It is the surrounding material glowing before it falls in. The light comes from the region outside the event horizon, where gas is dragged into a fast, hot, crowded disk called an accretion disk. This disk is the bright heart of the quasar. It is where gravity turns falling matter into radiation with almost unreasonable efficiency. Think of the accretion disk as a traffic jam around a cosmic roundabout, except the cars are clouds of plasma. The roundabout is a supermassive black hole, and nobody has any hope of politely merging into the correct lane. Gas spirals inward, but it cannot simply drop straight down. It has angular momentum, which means it wants to orbit, so it circles. Inner parts of the disk orbit faster than outer parts. Layers of gas rub against other layers. Magnetic fields twist through the material. The gas heats up until it emits huge amounts of light, especially ultraviolet light, and often X-rays closer to the center. The black hole sits inside all of this, not shining, not burning, not acting like a star, but providing the gravitational well that makes the whole engine possible. This is why quasars can be so bright. They're powered by gravity, and gravity near a supermassive black hole can release staggering amounts of energy. In a normal star like the Sun, light comes from nuclear fusion in the core, where hydrogen becomes helium. That is already impressive. It has kept Earth warm for billions of years, which is a rather good review for a natural energy source. But accretion onto a black hole can convert matter into radiation even more efficiently than ordinary stellar fusion. Not all the matter becomes light, of course. Much of it eventually crosses the event horizon. But before it vanishes, a significant portion of its gravitational energy can be released. The result is a central region that may outshine all the stars in its host galaxy combined. This is one of the most important ideas in the whole story. A quasar is not big because the glowing part is as wide as a galaxy. It is big in output, not necessarily in size. The light-producing region can be small compared with the galaxy around it, sometimes only light days, light weeks, or light months across for important inner regions. Yet it can be visible across billions of light years. It is a compact engine with a galactic-scale voice. If that feels odd, it should. It is one of those places where the universe reminds us that size and power are not always arranged the way common sense expects. A match is small and a mountain is large, but near a black hole, small regions can speak very loudly. Early astronomers did not know this at first. When quasars were first identified, they looked like stars in optical telescopes. They were point-like. They did not show the broad, fuzzy glow that astronomers expected from a galaxy. That is where the name came from: quasi-stellar radio sources at first, and then quasars, meaning star-like objects. But their light did not behave like ordinary starlight. When astronomers spread that light into a spectrum, they found emission lines shifted far toward the red. Those redshifts meant the objects were not nearby stars at all. They were extremely distant, and once that distance was understood, the brightness became astonishing. For a point of light to be visible from so far away, it had to be producing an enormous amount of energy. This must have been a quietly thrilling and slightly inconvenient moment in astronomy. Imagine thinking you have found a strange star, then realizing you have found the blazing center of a galaxy so far away that its light has spent much of cosmic history simply getting here. That is the sort of discovery that makes the universe feel larger overnight. It also created a question that demanded an engine. What could produce so much light from such a small region? Stars could not do it. Normal galaxies could not vary fast enough. Explosions could be bright, but they faded. Quasars could shine for long periods. The best explanation became accretion onto supermassive black holes. And over time, that idea became the foundation for understanding quasars as part of the wider family of active galactic nuclei. An active galactic nucleus, or AGN, is the active central region of a galaxy powered by a feeding supermassive black hole. Quasars are among the most luminous members of that family. The word active matters because a black hole can be present without producing a quasar. A galaxy can have a central black hole that is mostly quiet because little gas is falling in. It may still occasionally flare if a star or cloud wanders too close, but it will not shine as a quasar unless there is enough material feeding the disk. So a quasar is not just a thing. It is also a phase, a condition, a period in the life of a galaxy when the central black hole is being supplied with fuel and the surrounding region becomes brilliantly active. The fuel can come from gas already in the galaxy, or from events that disturb the galaxy and send material inward. Galaxy mergers are one possible trigger. When two galaxies pass through, or combine with each other, their stars usually do not collide directly because stars are tiny compared with the spaces between them. But gas clouds can be disturbed, compressed, and redirected. Gravitational interactions can pull material out of stable orbits and help it drift toward the center. Not every merger creates a quasar, and not every quasar requires a dramatic merger in a simple way, but disturbances in a galaxy can help feed the central black hole. The black hole itself may be small compared with the whole galaxy, but if gas begins moving inward, the center can wake up. That waking up is not like turning on a lamp with a switch. It is more gradual, messier, and more physical. Gas must lose angular momentum. It has to move from galactic scales, which are huge, down towards the central region, which is tiny by comparison. This is not easy. Matter in orbit tends to stay in orbit unless something helps it shed energy and momentum. Bars in galaxies, gravitational interactions, turbulence, collisions between gas clouds, and magnetic processes can all help move material inward. By the time gas reaches the accretion disk, it is entering a realm where gravity, heat, radiation, and magnetism all matter. The quasar is the bright result of a long delivery problem. The universe has to get the fuel from the wide galaxy down to the narrow mouth of the central engine. Around the disk there are other regions that help give quasars their recognizable fingerprints. Some gas moves in fast clouds relatively close to the black hole. This region can produce broad emission lines because the gas is moving at thousands of kilometers per second. When light from those atoms reaches us, the motion spreads the spectral lines out. Part of the gas is moving toward us, part away from us, part sideways, and the result is a widened feature in the spectrum. Farther out, slower moving gas can produce narrower lines. Dusty material may surround the central region in a thicker structure, often described as a torus, though real cosmic dust arrangements may be clumpy and complicated rather than a perfectly neat donut. This dusty structure can block certain views of the center. From one angle, we may see deep into the hot central disk and broad line region. From another, dust may hide parts of it, changing the type of object we think we're seeing. This leads to a useful point that will come back again and again. Quasar types are partly about what the object is doing, and partly about how we see it. The same central engine can look different depending on angle, dust, jet direction, and wavelength. If you view the active nucleus directly, it may appear as a bright quasar with broad lines. If your view is partly blocked, the broad line region may be hidden, and the object may look like a different kind of active galaxy. If a powerful jet is aimed near your line of sight, the brightness may be boosted and variable, producing a blazar-like appearance. If the jet points elsewhere, the same kind of engine may look much less extreme to us. Astronomy often depends on where we happen to be standing, and Earth is not exactly free to wander around the universe choosing better viewing angles. We work with the seat we were given. There is something almost theatrical about this. The central black hole and disk are the main stage, but curtains of dust, moving clouds, and narrow beams of jet light decide what the audience sees. From one seat, the show is open and bright. From another, half the stage is hidden. From another, a spotlight points directly into your eyes and makes the whole performance look much more intense than it would from the balcony. None of these views is completely false. Each one is incomplete in its own way. By comparing many quasars, astronomers reconstruct the full arrangement. The host galaxy is part of the story too, even when the quasar overwhelms it. In many distant quasars, the central light is so bright that seeing the surrounding galaxy becomes difficult. It is like trying to inspect a candlelit room while someone shines a searchlight through the window. Modern telescopes and careful image processing can sometimes separate the host galaxy from the quasar's glare, revealing disturbed shapes, star formation, mergers, or massive elliptical galaxies around the active centre. This matters because quasars are not isolated engines. They live in galaxies, and their activity can affect those galaxies. The influence can happen through radiation, winds, and jets. Radiation from the quasar can heat surrounding gas. Winds from the accretion disk can push material outward. Jets, when present, can carry energy far beyond the central region and into the galaxy, or even the space around the galaxy. This is often called feedback. It is not feedback in the sense of a microphone's squeal at a school assembly, though that may be the less terrifying version. In galaxy evolution, feedback means that energy from stars or active black holes affects the gas from which stars form. A quasar can help regulate growth. It may push gas away, heat it, stir it, or prevent it from cooling efficiently. In some situations, it may slow future star formation. In others, pressure from jets or outflows might compress gas and encourage stars to form in certain places. The details are complicated, but the central point is clear enough. A quasar is not simply a bright sign at the centre of a galaxy. It can participate in shaping the galaxy's future. That is one reason quasars are so important for understanding cosmic history. They were more common in the earlier universe, especially around the era when galaxies and black holes were growing rapidly. When we look at distant quasars, we're often seeing supermassive black holes in a younger universe, when there was more gas available and more intense galaxy building underway. This creates one of the great puzzles of quasar science. Some quasars seen at very high redshift already contain black holes with masses of hundreds of millions or billions of suns when the universe was still relatively young. How did they grow so quickly? Did they begin as unusually massive black hole seeds? Did they feed at very high rates? Did they grow through mergers? The answer is still an active area of research, and it matters because black holes are not just endpoints. They are part of the story of how structure formed. A quasar's light can also be used as a probe. Because quasars are so bright and distant, their light passes through intervening gas on its way to us. That gas absorbs specific wavelengths, leaving marks in the spectrum. By studying those marks, astronomers can learn about material between galaxies, including hydrogen clouds spread through the cosmic web. In this way, a quasar becomes a background lamp for studying things that would otherwise be hard to see. The quasar itself is interesting, but so is everything its light has crossed. One beam can carry information about the central black hole, the host galaxy, intergalactic gas, cosmic expansion, and the chemical enrichment of the universe. It is a long-distance message with several notes written in the margins. The spectrum also tells us the quasar's redshift, which tells us how much the universe has expanded since the light was emitted. This does not mean the quasar is simply moving away through ordinary space like a car on a road, though local motion can contribute a little. On the larger scales, space itself has expanded while the light travelled, stretching the wavelengths. Blue light can become redder. Ultraviolet light can be shifted into visible or infrared wavelengths. For very distant quasars, astronomers need infrared observations to study light that began in the ultraviolet, but arrived stretched by cosmic expansion. This is one of the reasons modern space telescopes are so valuable. They can study ancient objects whose original light has been moved into wavelengths that Earth's atmosphere may block, or that ground-based telescopes cannot observe as cleanly. It is worth pausing here with the word redshift, because it is one of those scientific terms that can sound dry until you realize what it really means. The light has been traveling for billions of years, and during that journey the universe has grown. The wave itself has been stretched by the changing scale of space. So when astronomers measure a quasar's redshift, they are not just getting a number, they are reading a record of cosmic expansion. They're seeing how far back in time the light began, how much the universe has changed since then, and where that quasar belongs in the long history of everything becoming more spread out. Because quasars are powered by feeding black holes, their brightness can change. Matter does not flow into the disk perfectly smoothly. There can be clumps, instabilities, hotspots, magnetic activity, and changes in the supply of gas. Some quasars vary over months or years. Some more compact and jet-dominated sources can vary much faster. This variability is useful. If an object changes brightness quickly, the region responsible must be relatively small, because information cannot travel faster than light. A large region cannot coordinate a rapid change all at once. So variability gives astronomers a rough size limit. The flicker becomes a ruler. It is rather pleasant, in a strange way, that the restlessness of a quasar helps reveal its scale. The black hole mass can be estimated in several ways, often using the motion of gas in the broad line region and the brightness of the source. The basic idea is that faster moving gas near the centre suggests a stronger gravitational field, and therefore a more massive black hole, if the size of the region can be estimated. There are uncertainties, and quasars are not polite laboratory objects arranged under controlled conditions. But with large surveys and careful calibration, astronomers can build a picture of black hole masses and feeding rates across cosmic time. This is how quasars become not just spectacular objects, but statistical tools. One quasar is a mystery. Many quasars become a population. A population can reveal patterns. A key measurement is how fast the black hole is feeding compared with a theoretical limit called the Eddington limit. This limit comes from a balance between gravity pulling matter inward and radiation pushing outward. If a source shines too intensely, radiation pressure can push gas away and make further accretion harder. Real systems can be more complicated, and some may accrete in ways that challenge simple limits, but the Eddington idea gives astronomers a useful scale. A quasar shining near this limit is feeding very actively for its mass. A lower luminosity active nucleus may be feeding more gently. Again, the black hole itself is not eating like an animal. It is not hungry in the emotional sense, but feeding is such a useful word that astronomy has allowed it to stay, probably because undergoing sustained gravitationally mediated accretion is less cozy before bedtime. There is another common misunderstanding worth clearing away softly. A quasar does not mean a black hole is swallowing an entire galaxy. The stars in the galaxy are not all spiralling into the centre like leaves down a drain. Most stars are far away and orbit safely. Space is large, orbits are stable, and black holes do not reach out with magical suction. The quasar is powered by material in the central region, especially gas. Even when a black hole grows by millions of solar masses, that is still a small fraction of a large galaxy's total mass. The quasar can influence the galaxy, but it is not simply devouring it whole. The real picture is more interesting than the cartoon version. Gravity organizes, gas flows, radiation fights back, magnetic fields launch structures, dust hides and reveals. The galaxy and black hole evolve together in a long exchange of matter and energy. In a way, a quasar is a contradiction that works. It is light from darkness. It is a compact object visible across cosmic distances. It is a sign of matter falling inward that can also drive matter outward. It is a central point that helps us study the vast spaces between galaxies. It is both an object and a tool, both a physical engine and a historical marker. This is why astronomers keep returning to them. They sit at the intersection of black hole physics, galaxy evolution, cosmic expansion, plasma physics, radiation, chemistry, and time. Not bad for something that once looked like a suspicious little star on a photographic plate. For our journey through every major quasar type, this shared engine is the foundation. whether we are talking about radio-loud quasars, radio-quiet quasars, broad-line quasars, narrow-line quasars, red quasars, blue quasars, blazars, optically violent variables, or broad absorption line quasars, we are returning again and again to the same basic arrangement. A supermassive black hole sits at a galactic centre. Matter falls inward and forms a hot accretion disk. Gas clouds respond to the radiation. Dust may block part of the view. Magnetic fields may help launch jets. Winds may blow outward. The observed type depends on how strong these features are, which wavelengths we observe, and what angle the universe has chosen for us. Some quasars do not merely glow, they throw. They take the energy of a feeding supermassive black hole and somehow organize part of it into long, narrow jets that can pierce far beyond the central region of the galaxy, far beyond the stars around it, and sometimes far into the space between galaxies. This is where radio-loud quasars enter the story. They are not called radio-loud because they make sound, of course. Space is not carrying a deep cosmic roar to us like thunder across a field. They are called radio-loud because when astronomers look at them with radio telescopes, they shine strongly in radio wavelengths. They announce themselves in a part of the electromagnetic spectrum our eyes cannot see, but our instruments can hear in their own careful way. That phrase, radio-loud, can sound almost charming, as if the quasar is the neighbour upstairs moving furniture at midnight. But the real meaning is much larger. A radio-loud quasar is usually a quasar with powerful jets, streams of high-energy particles launched from the central engine and guided by magnetic fields into narrow beams. These jets can move at nearly the speed of light. They can stretch thousands, hundreds of thousands, or even millions of light years from the centre of the host galaxy. In some cases, the radio structures connected to an active galaxy are much larger than the visible galaxy itself. The black hole may be hidden in the tiny central core, but the jet writes its signature across a much wider region, like a pen stroke so large it runs off the page. To understand why these objects are radio bright, we need to leave ordinary light for a moment and think about charged particles and magnetic fields. In a jet, electrons and other particles are accelerated to very high energies. As they spiral through magnetic fields, they emit a kind of radiation called synchrotron radiation. This radiation can be strong at radio wavelengths, though it can also appear in other parts of the spectrum depending on the particle energies and conditions. The important idea is simple enough. A jet is not just a stream of glowing gas. It is a magnetic, high-speed, particle-filled structure, and its moving charged particles create radio light as they curve and spiral. If an accretion disk is the bright whirlpool around the black hole, then the jet is the narrow escape route for some of the system's energy. The strange thing is that the black hole itself is still not letting anything escape from inside the event horizon. The jet is not coming out of the black hole's interior like water from a hose. That would break the rules, and black holes are very strict about their paperwork. Instead, the jet is launched from the region around the black hole, likely involving the inner accretion disk, the spinning black hole, and magnetic fields twisted into extreme configurations. The exact details of jet launching are still studied, but the broad picture is that rotation and magnetism work together to channel energy outward along the poles of the system. The disk feeds inward. The jet fires outward. The centre becomes a place where gravity pulls, heat shines, and magnetism finds a direction. It may help to picture the quasar engine as having a kind of axis, like a spinning top. Around the middle is the accretion disk where gas spirals inward. Above and below the disk along the rotation axis jets may emerge. They do not spread evenly in all directions. They are collimated, which means they are kept narrow, focused and organised over enormous distances. That is one of the most impressive parts. Anyone can imagine an explosion throwing material everywhere. It is much harder to imagine a structure that stays narrow while crossing distances larger than galaxies. The jet must remain guided by magnetic fields and its own motion, pushing through surrounding gas, forming knots, shocks, and bright regions where particles are accelerated again. Radio telescopes reveal this hidden architecture. In visible light, a quasar may look like a bright point. In radio images, a radio-loud quasar can show a core, a jet, and enormous lobes on either side of the galaxy. The lobes form where the jets finally slow down and dump energy into surrounding material. They can look like great inflated bubbles of radio-emitting plasma sitting far from the galactic centre. Sometimes the structure is roughly symmetrical, with a jet going one way and another jet going the opposite way. Sometimes one side looks brighter because it is pointed more toward us and its light is boosted by relativistic effects. The universe gives us geometry lessons whether we asked for them or not. This brings us to one of the most important ideas in radio-loud quasars: orientation. If a jet is pointed somewhat toward Earth, it can appear brighter than the jet pointing away from us. This happens because of relativistic beaming. When material moves close to the speed of light toward the observer, its radiation is concentrated and boosted in the forward direction. The approaching jet can dominate what we see. The receding jet may fade into the background or become harder to detect. This does not mean the quasar is actually launching only one jet. It means our view is affected by speed and direction. In the universe, as in ordinary life, where you stand can change the whole story. If the jet points almost directly at us, the object can enter the realm of blazars, which we will visit later. For now, with radio-loud quasars, it is enough to understand that jets can be seen from many angles. Side-on, they may show extended lobes and large radio structures. Closer to the line of sight, the central core may look brighter and more variable. This is why classification can be tricky. A radio-loud quasar is not simply a quasar with one fixed appearance. It is a powerful central engine plus jets, seen through the particular accident of our location. We are not choosing the angle, we are receiving the angle. The term radio-loud also has a historical flavour. When quasars were first being understood, some were discovered through radio surveys because they were strong radio sources. One of the famous early quasars, 3C273, became a key object in the history of quasar discovery. It looked star-like, but its spectrum revealed a large redshift, placing it far beyond the Milky Way and making its true luminosity extraordinary. Radio astronomy helped open the door to this realization. In a way, radio-loud quasars were among the first loud knocks on the door, telling astronomers that something very strange was happening at the centres of distant galaxies. The knock did not sound in human ears. It arrived as radio waves and spectral lines, and it changed astronomy anyway. The distinction between radio-loud and radio-quiet sounds simple, but nature has made it less tidy. Traditionally, astronomers often used a ratio between radio emission and optical emission to decide whether a quasar counted as radio-loud. If the radio output was strong enough compared with the visible light, it went into the radio-loud category. That was useful, especially when surveys were smaller and categories needed practical boundaries. But as radio telescopes have become more sensitive, astronomers have found that many quasars may have some radio emission, and the difference between loud and quiet can look more like a broad range than a perfectly clean split. Some objects are dramatically radio-loud, no question at all. Others sit in between. The universe rarely reads our classification manuals before forming things. Still, the strongest radio-loud quasars are unmistakable. They show powerful jets and large-scale radio structures that reveal an active central engine capable of launching energy far from the galaxy's core. These jets are not decorative. They can affect the environment around the galaxy. As they push outward, they disturb gas, inflate cavities, drive shocks, and deposit energy into regions that might otherwise cool and form stars. In galaxy clusters, radio jets from active galaxies can heat the hot gas between galaxies and help prevent it from cooling too quickly. In individual galaxies, jets may regulate star formation by stirring or heating gas, or sometimes by compressing gas in certain regions. Feedback is a plain word for a complex exchange. The black hole feeds, the jet pushes, the galaxy responds. It is remarkable that a black hole, which may be tiny compared with its host galaxy, can influence such large surroundings. A supermassive black hole's event horizon may be only a small central boundary on galactic scales, but the energy released by accretion and carried by jets can spread outward across huge distances. This is one reason radio-loud quasars are so important. They show us that black hole growth and galaxy evolution are connected. The black hole does not simply sit in the middle like a heavy ornament. When it is active, it can become a kind of regulator, engine and weather system for the galaxy's gas. Not weather in the ordinary sense, of course. No clouds with umbrellas, no forecast presenter calmly saying there is a chance of relativistic plasma by afternoon. But in a galactic sense, jets are part of the climate. The jet's path is not always perfectly straight. Some radio jets bend, twist or show knots along the way. These shapes can be caused by interactions with surrounding gas, changes in the direction of the central engine, movement of the host galaxy through its environment, or instabilities in the jet itself. A knot in a jet may mark a shock where particles are reaccelerated and the jet brightens. A bend may show that the jet has encountered resistance, or that the central launch direction has shifted over time. The large radio lobes preserve a history of activity, almost like tree rings made of plasma. They can tell astronomers not only that the quasar is active now, but that it has been shaping its surroundings over long spans of time. Some radio galaxies show jets extending from central active nuclei but are not necessarily observed as quasars, often because of orientation, luminosity or obscuration. This is where the wider AGN family becomes useful again. Quasars, radio galaxies, blazars and other active nuclei may be related through underlying structures viewed differently. A radio-loud quasar may be the bright direct view of an active central engine with strong jets. A radio galaxy may show similar jets but with the central quasar-like light blocked or less dominant from our angle. A blazar may be the jet pointed close to us, making the object appear extremely bright and variable. These are not always separate machines. Often they're related machines wearing different observational faces. For a listener drifting towards sleep, this might be compared to a lighthouse on a foggy coast, though the comparison is very small beside the real thing. If you stand in the path of the beam, it flashes bright and sharp. If you stand to the side, you see the glow less directly. If fog lies between you and the lamp, the whole structure changes again. The lighthouse is the same, but the view changes. A radio-loud quasar is more complicated than a lighthouse, and much less suitable for seaside postcards, but the central idea remains: beams, angles, and intervening material matter. The radio emission from a quasar can also help astronomers locate and study objects that are difficult to understand in visible light alone. Radio waves can pass through dust better than visible light, so radio observations can reveal jets and cores hidden from optical telescopes. Very long baseline interferometry, a technique that links radio telescopes across large distances, can produce extremely high-resolution images of compact radio structures. This allows astronomers to study jet motion, core brightness, and fine details that would otherwise blur together. With radio interferometry, Earth itself can become part of the telescope, its separated dishes working together like a single instrument nearly the size of the planet. That is a nice thought to take into the night. A small rocky world quietly rearranging its radio ears to listen to black holes across the universe. The jets also raise a question that is still not completely settled. Why are some quasars so radio loud while others are not? If many quasars have accretion disks and supermassive black holes, what decides whether a powerful jet forms? Several factors may matter. Black hole spin could be important, because a rapidly spinning black hole may help supply energy to the jet through magnetic fields. The structure and magnetic strength of the accretion flow may matter. The mass of the black hole may matter. The environment around the galaxy may affect how visible or extended the jet becomes. It may not be one single switch marked jet and no jet, which would be convenient but rather unrealistic. It is probably a mixture of conditions. The universe tends to prefer dials over switches. Radio-loud quasars are especially valuable in the distant universe because they can serve as bright beacons across enormous stretches of space and time. Some are seen when the universe was much younger, and their jets tell us that supermassive black holes were already not only growing, but launching powerful outflows early in cosmic history. That creates more questions. How did those black holes become massive enough so quickly? How did their jets interact with young galaxies still rich in gas? Did jets help regulate the formation of early stars, or did they stir young galaxies into even more complicated behaviour? Each distant radio-loud quasar is a clue from a time when the universe was still building many of its largest structures. There is also a practical reason astronomers care about radio-loud quasars. Because some are bright and compact in radio wavelengths, they can be used as reference points for precise measurements of positions in the sky. Quasars are so far away that their apparent motions are usually extremely small, making them useful anchors for celestial coordinate systems. In other words, objects powered by restless black holes can help us define stillness. That feels slightly absurd, but astronomy is full of these little reversals. The most violent distant engines can become fixed points on our maps. The universe has a sense of humour, even if it delivers the joke through interferometry. As with all quasars, radio-loud quasars remind us that we are seeing both space and time. A jet that appears hundreds of thousands of light-years long is not a single frozen object in the ordinary sense. Light from different parts reaches us after different travel times. The jet itself may change, brighten, fade, or shift over long periods. The large radio lobes may show older activity, while the bright core shows what is happening closer to the central engine at a different stage. Looking at a radio-loud quasar is like reading several pages of history at once, with the ink arriving from different distances. Astronomers disentangle this with models, maps, spectra, and patient comparison. The physical scale is difficult to hold in the mind. A jet may begin in a region around a black hole smaller than the solar system, then travel farther than the width of a galaxy. That is a scale jump so enormous, it almost stops feeling real. It would be like something beginning at the size of a teacup and drawing a line across a continent, except even that is too small by far. The jet stays connected to the central engine through physics, not through a visible pipe or solid structure. It is a flow of particles, energy, and magnetic fields, moving through space with astonishing persistence. The central black hole does not need to be large in diameter compared with the galaxy. It only needs to be efficient at turning accretion and rotation into directed power. If we could see radio waves with our eyes, the night sky would be a very different place. Some galaxies that look modest in visible light would show enormous radio lobes. Some quasars would no longer be tiny points, but sources with vast structures spreading across the darkness. The sky would look less like a quiet field of stars, and more like a map of engines, beams, bubbles, and old outbursts. Luckily for sleep, our eyes do not see radio waves directly. The visible night remains mostly calm, while radio telescopes do the noisier work on our behalf. Radio-loud quasars also help explain why one wavelength is never enough. If astronomers only used visible light, they might miss the scale of the jets. If they only used radio waves, they might miss details of the accretion disk, broad emission lines, or host galaxy. X-rays reveal hot regions close to the black hole and high-energy processes in jets. Infrared light can show dust warmed by the quasar and sometimes reveal hidden activity. Ultraviolet light, when accessible or redshifted into observable bands, can reveal the hot disk and ionized gas. A quasar is a multi-wavelength object. It does not tell its story in one colour. It uses the whole orchestra. The radio-loud quasars have a particularly strong brass section. As dramatic as jets are, they do not mean the quasar is active forever. Quasar activity depends on fuel. A black hole can have active phases and quieter phases. The jets may turn on, weaken, restart, or change direction over cosmic time. Some radio sources show evidence of repeated activity, with older lobes and newer jets suggesting more than one episode of feeding. The galaxy centre may not be a steady engine running at one constant speed. It may be more like a machine that wakes when supplied, quiets when fuel runs low, and wakes again when new gas reaches the centre. Across millions of years, that rhythm can leave huge marks. For all their power, radio-loud quasars are not the majority of quasars. Many quasars are radio quiet by traditional measures, meaning they do not produce radio emission, a strong relative to their optical light. This difference matters because it tells astronomers that powerful jets are not an automatic result of every feeding supermassive black hole. The central engine can blaze without launching a giant radio structure. That leads to the next natural question. If radio-loud quasars are the ones with jets that pierce deep space, what about the quasars that lack those dramatic radio beams? Are they truly quiet, or are they simply powerful in a different language? A quieter quasar is still not quiet in any normal sense of the word. It is only quiet when compared with the ones we just visited, the radio-loud quasars with jets long enough to write across intergalactic space. This is one of those moments where astronomy uses a word very gently and then expects us not to be misled by it. A radio-quiet quasar can still outshine its entire host galaxy. It can still pour out ultraviolet light, optical light, infrared light, and X-rays. It can still heat dust, shake gas, drive winds, and mark the early universe like a bright pin on a very old map. Quiet, here, simply means that it does not have the same kind of dominant, giant, radio-bright jet that makes a radio-loud quasar so easy to notice in radio surveys. So if radio-loud quasars are the ones that seem to throw narrow beams across deep space, radio-quiet quasars are the ones that remind us that the central engine does not need those beams to be powerful. Their strength is hidden in a different place. It is in the accretion disk, in the hot inner gas, in the radiation pouring from the region around the supermassive black hole, and often in winds that are harder to picture than jets, but just as important for understanding how galaxies live and change. They are not silent engines. They are engines speaking in another language. The basic heart is the same. A supermassive black hole sits in the centre of a galaxy. Gas falls inward. Because the gas has angular momentum, it does not plunge straight down. It spirals into a disk orbiting faster as it approaches the centre. Friction, turbulence, and magnetic processes heat the gas until it shines. Closer in, the temperatures rise high enough to produce X-rays. Farther out, dust absorbs part of the radiation and re-emits it in infrared light. Gas clouds around the nucleus glow with emission lines. From a distance, if the central engine is bright enough, the whole galaxy may look like a star-like point with a spectrum that reveals its true nature. That is a quasar, even without a giant radio jet. This matters because most quasars are not radio-loud. The radio-loud ones are spectacular, and they were historically important in the discovery of quasars, but they are not the whole family. Many quasars shine mainly because of the accretion disk and the surrounding gas, not because of a huge relativistic jet. These objects may have weak radio emission, compact radio cores, small-scale outflows, or hints of faint jet activity, but their radio output is much smaller compared with their optical or ultraviolet brightness. A radio-quiet quasar is not necessarily radio-silent. It is more like a person at a dinner table who's not whispering exactly, but is sitting next to someone with a megaphone. That comparison is useful because the name can make radio-quiet quasars sound less dramatic than they are. In reality, they may be some of the best places to study the pure radiative power of a feeding black hole. Without a huge jet dominating the view, astronomers can focus more clearly on the accretion disk, the corona that produces X-rays, the broad-line gas moving near the black hole, and the winds that flow outward from the disk. In a radio-loud quasar, the jet can be so bright that it complicates everything. In a radio-quiet quasar, the disk and its surrounding structures often take center stage. A good real example is PDS 456. It is one of the most famous nearby luminous radio-quiet quasars, and nearby here still means far beyond any human reach. It sits at a redshift of about 0.184, which makes it relatively close in quasar terms, not in weekend trip terms. PDS 456 is especially interesting because it is extremely bright and has powerful outflows. Astronomers have studied it in X-rays and other wavelengths and found evidence for gas racing outward at a significant fraction of the speed of light. This is important because it shows that a radio-quiet quasar can still send enormous energy back into its surroundings. It may not be carving space with a giant radio jet, but it can still blow a wide, fast wind from the region near the accretion disk. That wind is not like air moving through trees, of course. It is highly ionized gas, heated and stripped of many of its electrons, moving under the influence of radiation, magnetic fields, and gravity near a supermassive black hole. When this gas lies along our line of sight, it absorbs certain X-ray wavelengths, leaving marks in the spectrum. Those marks are shifted because the gas is moving so quickly. Astronomers can read that shift and estimate the speed of the outflow. PDS 456 has become one of the key objects for studying these ultra-fast outflows, and it helps show that radio-quiet quasars are not passive. They can push back against the galaxy around them. This is one of the central ideas in radio-quiet quasars. Without the obvious radio jet, the feedback may come through radiation and winds. The quasar shines on surrounding gas. Its light carries momentum. The accretion disk can launch outflows. Those outflows can move into the host galaxy, possibly disturbing or removing gas that might otherwise form stars. The process is messy, and not every object behaves the same way, but the possibility is important. A central black hole, through a bright quasar phase, may help regulate the growth of its galaxy even when it is not sending out huge radio lobes. There is a small comfort in knowing that power does not always need a visible spear. A jet is easy to imagine because it has direction. It points, it stretches, it draws a line. A wind is subtler. It can be wide, clumpy, uneven, sometimes hidden, sometimes only visible because of what it absorbs. Yet winds may carry enough energy and momentum to matter on galactic scales. In PDS 456, observations have suggested not only fast X-ray winds near the central region, but also larger-scale molecular outflowing gas in the host galaxy. That gives astronomers a chance to connect the small and large pictures, the inner black hole engine, and the wider galaxy that must live with its consequences. Another real example is PG 1211+143. This is a bright, well-studied quasar that has also become important in the study of high-velocity outflows. It is not famous because it has a huge radio jet dominating the sky. It is famous because its X-ray spectrum has revealed signs of ionized gas moving outward at very high speed. Like PDS 456, it helps astronomers study the connection between the accretion disk and the winds that may carry energy away from the black hole. PG 1211+143 is a reminder that some of the most interesting quasar behavior is not found in giant radio structures, but in the detailed fingerprints of gas close to the center. Those fingerprints require patient work. A telescope collects X-rays, ultraviolet light, optical light, and sometimes radio data. Spectra are built. Lines are identified. Absorption features are compared with known atomic transitions. If a feature appears at a wavelength different from where it would normally be, astronomers ask why. Is the gas moving toward us or away from us? Is the whole quasar redshifted by cosmic expansion? Is an outflow adding its own blue shift on top of that? The answer is not simply read off like a label on a jar. It is reconstructed through models, repeated observations, and careful checks. Quasar wines are not polite enough to introduce themselves clearly. PG 1211 plus 143 also shows why radio-quiet quasars can be excellent laboratories for accretion physics. The X-ray light comes from very close to the black hole, likely from a hot corona near the inner disk. The ultraviolet and optical light can come from somewhat farther out in the disk. Winds may rise from the disk and cross our line of sight. Changes in X-rays and ultraviolet light can reveal how different parts of the system respond to one another. This means astronomers can use variability as a kind of map. They cannot resolve the inner disk directly in ordinary images because it is much too small and much too far away. But if one region brightens and another responds later, that time delay becomes a clue to distance and structure. This is one reason quasars are so useful despite being unreachable. They change, they flicker, their spectra shift, their winds appear stronger or weaker, their X-ray brightness rises or falls. Every change is a clue. The quasar is too far away to touch, but it is not frozen. It is an active machine, and by watching it over time, astronomers can infer the arrangement of parts too small to see directly. In that sense, radio-quiet quasars are not dull at all. They are full of motion hidden inside light. There are other well-known radio-quiet quasars and quasar-like active galaxies that add to this picture. MR2251-178, for instance, is often discussed as a radio-quiet quasar and is historically notable in X-ray studies. It has shown warm absorber features, meaning ionized gas along the line of sight affects the X-ray spectrum. Objects like this help build the broader story of how gas near active black holes can absorb, emit, and flow. Some of that gas may be close to the nucleus, some may be farther out, some may be part of a disk wind. Some may belong to a more extended environment. The quasar is not just a point of light. It is a layered system of regions, each leaving its mark. This layered structure is one reason radio-quiet quasars can be difficult to classify neatly. If the central engine is seen directly, the quasar may show broad emission lines from fast gas near the black hole. If dust blocks some of the inner region, the spectrum changes. If an outflow lies in our line of sight, it may create absorption features. If the host galaxy contributes light, that can complicate the picture. If the quasar is distant, cosmic redshift moves important wavelengths into different observing bands. It is rather like listening to a conversation through several walls while the room itself is moving away from you, and someone has placed a warm lamp in front of the transcript. Astronomy makes progress anyway, which is honestly quite impressive. The radio-quiet category also raises the question of why some quasars produce giant jets and others do not. Since both radio-loud and radio-quiet quasars involve accreting supermassive black holes, there must be additional factors. Black hole spin may matter, the magnetic field structure near the black hole may matter, the thickness and state of the accretion flow may matter. The amount of magnetic flux gathered near the centre may be important. The host galaxy environment may influence whether a jet grows large and remains visible. It is possible that some radio-quiet quasars have weak or frustrated jets that never develop into enormous radio structures. Perhaps the central engine tries to launch something, but the outflow stalls, disperses, or remains compact. The difference may not be a clean yes or no question. It may be a whole range of possible engine states. This is a useful place to slow the mind a little. A black hole is simple in the mathematical sense, described by mass, spin and charge, though astrophysical black holes are surrounded by anything but simple conditions. The quasar environment adds gas, dust, plasma, magnetic fields, radiation pressure, turbulence and motion. Two black holes with similar masses may behave differently if their disks and magnetic fields are different. Two quasars with similar optical brightness may differ enormously in radio power. The central object matters, but so does the material that feeds it and the environment that shapes the outflow. A quasar is not just a black hole. It is a black hole plus its meal, its weather, its magnetic machinery, and the galaxy around it. For radio-quiet quasars, the absence of a huge radio jet lets the thermal emission from the accretion disk become especially important. Many quasars show what astronomers call a big blue bump in their spectral energy distribution, a strong rise in optical and ultraviolet emission thought to come from the hot accretion disk. This feature is one of the signs of the disk's radiative power. The disk is not glowing at one simple temperature, like a household bulb. Different parts of it have different temperatures. Inner regions are hotter. Outer regions are cooler. Together, they create a broad spectrum of light. X-rays may come from the corona, a hot region of energetic electrons that interacts with disk photons and boosts them to higher energies. Dust farther out absorbs some of the ultraviolet and optical radiation and re-emits it in the infrared. The quasar becomes a set of connected zones, each translating the central energy into a different kind of light. The dusty region matters as well. Even in radio-quiet quasars, dust can shape what we see. Dust near the nucleus may be heated until it glows in the infrared. If our view passes through dusty material, the quasar can appear redder or more obscured. Some quasars may look different not because the engine is fundamentally different, but because the line of sight crosses different amounts of dust. This will become especially important when we talk about red quasars and blue quasars later. The colour of a quasar is not merely decoration. It can reveal temperature, dust, distance, and the route the light has taken before reaching us. Radio-quiet quasars also help clarify the relationship between quasars and Seyfert galaxies. Seyfert galaxies are active galaxies usually found at lower luminosities than quasars, and many are radio-quiet. The boundary between a bright Seyfert nucleus and a low luminosity quasar can be partly a matter of brightness and context. Both are powered by accretion onto supermassive black holes. Both can show broad and narrow emission lines. Both can have X-ray coronae, dusty structures, and winds. Quasars are the more luminous end of the family, the ones bright enough to be seen across great cosmic distances and sometimes overwhelm the light of the host galaxy. This continuity is helpful because nearby Seyfert galaxies can be studied in more detail, while distant quasars show the same basic physics operating at grander scales and earlier times. There is also something important about the word hidden in this section's title. The power of radio-quiet quasars is hidden not because it is weak, but because it is less visually obvious in radio maps. A giant radio jet gives you a structure you can point to. A disk wind gives you absorption lines. A hot corona gives you X-ray variability. A dusty torus gives you infrared emission. A broad line region gives you widened spectral lines. The hidden power is revealed through careful measurement, not through one dramatic shape. It is the difference between seeing lightning in the sky and detecting pressure changes before a storm. Both tell you something is happening, but one makes a louder entrance. PDS 456 is a good example of hidden power becoming visible through winds. PG 1211 plus 143 is another, with its high-velocity ionized outflow. These names may look like catalogue labels, and they are, but each label points to a real object, a galaxy with a central black hole, a disk of hot gas, and a surrounding environment marked by radiation and motion. Catalogue designations can feel cold until you remember that they are coordinates in a story. PDS 456 is not just a name in a table. It is a luminous, radio-quiet quasar whose outflows help us study quasar feedback. PG 1211 plus 143 is not just a string of letters and numbers. It is a nearby bright quasar whose X-ray behaviour helps us understand winds and accretion around massive black holes. From Earth, these objects arrive as light on detectors. A few photons are counted, a spectrum is drawn, a line is shifted, a model is tested. It sounds delicate because it is. Yet from that delicate evidence, scientists infer matter moving at tens of thousands of kilometers per second, gas heated to extreme temperatures, and black holes with masses millions or billions of times that of the Sun. Astronomy often works like this. Tiny measurements reveal enormous events. A small wiggle in a line becomes a wind from a quasar. A faint radio signal becomes a clue about whether a jet is present. A delay between wavelengths becomes a measurement of a disk too small to image. Radio-quiet quasars may also be easier places to study the relationship between radiation pressure and outflows. If the disk is extremely luminous, its light can push on gas. Electrons scatter photons. Ions absorb specific wavelengths. Dust, if present farther out, can feel radiation pressure too. Under the right conditions, radiation can help lift material from the disk and drive it outward. Magnetic forces may also contribute. The exact launching mechanism can vary, and astronomers continue to test different models. But the presence of fast winds in objects like PDS 456 and PG 1211+143 shows that outflowing gas is a real and important part of the radio-quiet quasar picture. This is also where the quiet category becomes almost misleading. A radio-loud quasar may send energy into space through a narrow jet. A radio-quiet quasar may send energy through radiation and winds over wider angles. One is not simply powerful and the other weak. They are different modes of black hole feedback. One writes with a sharp pencil. The other may press with a broad hand. The surrounding galaxy can feel both, depending on the strength, direction, and duration of the activity. A short-lived wind may disturb nearby gas. A long-lived outflow may affect star formation over larger regions. A luminous quasar phase may clear dust and gas from the center, changing how the galaxy looks afterward. There is a larger evolutionary idea here, though it should be held gently because real galaxies are complicated. Some models suggest that quasars may pass through stages. A gas-rich galaxy merger or disturbance could feed the central black hole while also surrounding it with dust. The quasar may be hidden or reddened at first. As radiation and winds push material away, the quasar becomes more visible, perhaps appearing as a blue, unobscured quasar. Later, the fuel supply may decline, and the active phase fades. Not every quasar follows this simple sequence, and nature is rarely so tidy. But radio-quiet quasars with strong winds are important pieces of this possible story. They may show us how a growing black hole helps clear its own surroundings. For the listener, maybe the simplest way to hold radio-quiet quasars in mind is this. The lack of a giant radio jet does not remove the engine. The black hole is still there. The disk is still bright. The gas is still moving. The radiation is still intense. The winds may still be fast enough to reshape the inner galaxy. The quasar may still be visible across billions of light years. It is quiet only in the radio sense, and only compared with the dramatic jet makers. It's quiet the way a volcano might be quiet if it is not also playing a trumpet. The light from a quasar is not just bright, it is marked. It carries little signatures from the gas around the central black hole, and those signatures tell us that the region near the black hole is not calm, not still, and certainly not arranged like a quiet lamp on a table. The gas there is moving fast, very fast. Fast enough that when atoms in that gas emit light, the fingerprints they leave in the spectrum are stretched and widened. This is where broad-line quasars come into view. They are quasars whose spectra show broad emission lines, and those broad lines are one of the clearest ways astronomers know that they are looking at gas racing in the deep gravitational neighbourhood of a supermassive black hole. To understand why this matters, it helps to return for a moment to the idea of a spectrum. When astronomers take the light from a quasar and spread it out, they are not only making a rainbow. They are opening a record of physical conditions. Certain atoms and ions emit light at specific wavelengths. Hydrogen has its patterns, carbon has its patterns, Magnesium has its patterns. Oxygen, nitrogen, helium, and many others have their own recognizable marks. In a quiet laboratory on Earth, those marks are narrow and predictable. They appear where physics says they should appear. But in a quasar, the lines can become wide, swollen, and stretched across a range of wavelengths. That broadening is not random decoration. It is motion written into light. The reason is the Doppler effect. You already know a familiar version of it from sound. When an ambulance moves toward you, the siren sounds higher. When it moves away, the sound drops lower. Light behaves in a related way. Gas moving toward us shifts its light slightly toward shorter, bluer wavelengths. Gas moving away shifts its light toward longer, redder wavelengths. In the broadline region of a quasar, there are clouds and streams of gas moving in many directions at once. Some gas is coming toward us, some is moving away. Some is orbiting across our view. Some may be rising in winds. All of that motion spreads the emission line out. Instead of one narrow mark, the spectrum shows a broad feature, as if the line has been pulled open by speed. That broadness tells us the gas is close to the black hole. Not inside the event horizon, of course. Nothing inside that boundary sends us a friendly emission line on the way out. The gas-producing broad lines remains outside the point of no return. But it is close enough to feel the black hole's gravity strongly. The closer gas orbits to a massive object, the faster it must move to stay in orbit. Around a supermassive black hole, those speeds can reach thousands of kilometers per second. That is not a slight breeze. That is gas moving so quickly that ordinary comparisons begin to give up and make tea. The region where this happens is called the broadline region, or BLR. It is not a solid shell or a tidy ring. It is more like a complex zone of dense gas clouds, streams, and possibly disc-shaped or wind-shaped structures around the central engine. It sits outside the very hottest inner accretion disk, but still much closer in than the larger narrow line region. The gas is close enough to move at tremendous speeds, and dense enough to produce strong emission lines when it is lit up by radiation from the accretion disk. The central continuum, the bright light from the hot disk and nearby regions, shines outward and ionizes the gas. Electrons are stripped from atoms. They later recombine or change energy states, and light is emitted. That light carries the line signatures astronomers study. A broad-line quasar, then, is not broad because the whole galaxy is smeared out. It is broad because the spectral fingerprints of gas near the black hole are widened by motion. The galaxy may be enormous. The broad-line region may be tiny by comparison. Yet that smaller region gives astronomers some of the most valuable clues in the entire quasar. It tells us about speed. Speed tells us about gravity. Gravity tells us about mass. In a careful way, broad lines help astronomers estimate the mass of the central black hole. That is quite a lot of information to receive from a widened mark in a rainbow. Imagine looking at a whirlpool from far away. You cannot see individual leaves caught in it, but if you could measure how fast the leaves were moving, you could learn something about the pull at the centre. A quasar's broadline region works a little like that. Astronomers cannot usually take a direct photograph of the gas clouds orbiting near a distant black hole. The angular sizes are far too small, but the gas reveals itself through its motion. The broader the line, the faster the gas is moving. If astronomers can estimate the size of the region as well, they can infer the black hole's mass using the relationship between orbital speed, distance, and gravity. The spectrum becomes a measuring tool. One of the most important methods for estimating the size of the broadline region is called reverberation mapping. It sounds like something you might do in a cave with an echo and a notebook, and actually the basic idea is not too far away. The central accretion disk changes brightness. Sometime later, the gas in the broadline region responds, because the change in radiation has travelled outward at the speed of light and altered the gas emission. By measuring the delay between the change in the central light and the response in the emission lines, astronomers can estimate the distance between the disk and the broadline gas. The delay is a light travel time. A response after 10 days suggests a region about 10 light days away. A response after 100 days suggests something larger. The quasar flickers, the gas answers, and the delay becomes a ruler. That is a wonderfully practical idea. Nobody has to fly to the quasar. Nobody has to drop a tape measure near a supermassive black hole, which would be a poor career decision. Instead, astronomers watch the light change and wait for the echo in the gas. It requires patience, repeated observations, careful calibration, and a willingness to let the universe answer at its own pace. The result is a way to map regions much too small to see directly. Reverberation mapping has become one of the key tools for studying active galactic nuclei and their central black holes. Broadline quasars are often described as unobscured or Type 1 active galactic nuclei in the wider AGN classification. That means our view reaches the central regions well enough that we can see the broadline gas directly. If dusty material blocks our line of sight, those broad lines may be hidden, and the object may look like a narrow-line quasar or a different obscured active galaxy. This is why broadline quasars are partly a matter of geometry. The broadline region may be present in many active galactic nuclei, but whether we see it depends on the angle and the material between us and the centre. The quasar is not changing its nature just to confuse us, although sometimes it does feel that way. We're simply seeing it from one particular line of sight. The broad lines themselves can come from different elements and ionization states. Hydrogen lines are common and important. The Lyman alpha line in ultraviolet light is especially significant in distant quasars, though cosmic redshift can move it into visible or infrared wavelengths by the time it reaches us. The H-beta line is widely used in lower redshift studies. Magnesium-2 and carbon-4 lines are also important for estimating black hole masses in quasars at different redshifts. Each line forms under somewhat different conditions and in somewhat different parts of the broadline region. That means the gas is not one simple zone. It has structure. Some parts are more highly ionized, some are denser, some may sit closer to the disk, some may belong to winds flowing outward. The broadline region is less like a neat ring and more like a crowded, glowing weather system near a black hole. The word clouds is often used for BLR gas, but we should be careful with it. These are not fluffy white clouds drifting gently across a blue sky. They're dense pockets or streams of gas in an environment flooded with radiation and shaped by gravity. They may be part of a clumpy distribution. They may be connected to the surface of the accretion disk. They may be launched in a wind. They may have flattened, disk-like motion, random motion, inflow, outflow, or some mixture of all of these. Astronomers debate the details because the broadline region is hard to image directly. We know it exists because the lines are there. We know it moves fast because the lines are broad, but the exact shape can vary between objects and remains an active research topic. One of the classic examples that helped define quasar science is 3C273. It is one of the brightest quasars in the sky, and one of the first to have its large redshift recognized. It is also a broad-line quasar, showing strong emission features connected with fast-moving gas near its central black hole. In recent years, astronomers have studied the broadline region of 3C273 with extremely precise interferometric techniques, finding evidence that the gas is orbiting in a disk-like structure around a black hole of hundreds of millions of solar masses. That is remarkable because the broadline region is tiny on the sky. It is not something a normal telescope image can simply resolve. Yet with enough precision, enough cleverness, and enough patience, astronomers can begin to see not just that the gas is fast, but how it is moving. 3C273 also reminds us that a quasar can belong to more than one descriptive category. It is radio loud because it has a jet and strong radio emission. It is also broad line because its spectrum reveals fast gas near the black hole. These categories are not always separate boxes, they overlap. A quasar can be radio loud and broad line, another can be radio quiet and broad line, another can have broad absorption lines as well. The universe does not mind wearing several labels at once. Human filing systems are the ones that get tired. The broadline region is especially useful because it sits between two extremes. On the inside is the accretion disk and the very compact X-ray emitting region, areas so close to the black hole that the physics becomes intense and difficult to observe directly. Farther out is the narrow line region, where gas moves more slowly and can extend across much larger scales. The broad line region sits in the middle, close enough to reveal the black hole's gravity, but not so close that all the information is lost in the glare of the innermost disk. It is like a ring of witnesses standing near the scene, close enough to describe the action but far enough away to still send us a message. When astronomers use broad lines to estimate black hole mass, they often rely on a virial assumption. In simple terms, if the gas is mostly controlled by the black hole's gravity, then its speed and distance from the centre can be used to estimate the mass inside its orbit. Faster gas at a given distance means more mass. Gas at a larger distance moving at a certain speed implies a different mass. In practice, there are correction factors because the geometry and orientation of the broadline region matter. If we view a flattened disk face-on, the line widths may look different than if we view it edge-on. Winds can also complicate the interpretation. Science does not simply take one number and declare victory. It asks how the number may be biased, then spends several decades politely worrying about it. Still, broadline measurements have become essential for studying quasars across cosmic history. For very distant quasars, astronomers often cannot perform detailed reverberation mapping because the observations are too difficult or time-consuming. Instead, they use single-epoch spectra, combining the width of a broad line with the quasar's luminosity to estimate the size of the broadline region and then the black hole mass. These estimates are not perfect, but they allow astronomers to study huge samples of quasars and ask how supermassive black holes grew over billions of years. The broad line becomes a cosmic weighing tool, not a bathroom scale, thankfully, more like a gravitational clue hidden in a stretched fingerprint. This is especially important for the early universe. Some quasars seen at high redshift already contain black holes with masses of 1 billion suns or more. Broad emission lines help establish those masses. That creates the famous growth problem. How did such massive black holes form so soon after the Big Bang? Did they begin from the collapsed remnants of the first stars and grow rapidly? Did they form from direct collapse of massive gas clouds into larger seed black holes? Did repeated mergers help? Did some feed at rates near or above the usual theoretical limits? The broad lines do not answer every question, but they show us the scale of the problem. The gas is moving fast because the central mass is enormous. The young universe had already built monsters. There is also a relationship between broad lines and quasar brightness. The central disk emits intense radiation, and that radiation ionizes the BLR gas. If the central continuum changes, the line strength can change. Different lines may respond differently depending on where they form and how the gas is arranged. This response lets astronomers study the structure of the region in more detail. A line that responds quickly may come from closer in. A line that responds more slowly may come from farther out. The broad line region is not seen directly, but it can be timed. Time becomes a map. That idea has a nice connection with the overall mood of this journey. We are studying some of the brightest objects in the universe by noticing delays, widths, and shifts. Huge cosmic engines become understandable through small changes in light. A line grows wider. A response arrives later. A wavelength moves slightly. These are quiet measurements of violent places. It is astronomy at its most patient. The black hole does not explain itself. The gas does not sit still. The light travels for billions of years. And on Earth, someone compares spectra and slowly reconstructs the arrangement. Broad line quasars can also show complex line shapes. Not every broad line is a smooth, simple hill. Some have asymmetries, wings, shoulders, or shifts. A line may be stronger on the blue side, suggesting outflowing gas. It may be red-shifted in a way that suggests inflow or gravitational effects. Some active nuclei show double-peaked broad lines, which can indicate emission from a disk where one side is moving toward us and the other away from us, though other explanations can exist. These shapes are valuable because they reveal that the BLR is not just a random swarm. Its motion has structure. It may include rotation, turbulence, inflow, outflow, and changing illumination from the central source. The connection between broad lines and winds is especially important. In some quasars, high ionization lines like carbon-4 can be shifted toward the blue, suggesting that part of the gas is flowing outward. This tells us that the broad line region may not be purely orbiting material. Some of it may be part of a disk wind rising from the accretion disk. That wind can absorb and emit light, and in stronger cases it may connect to the broad absorption line quasars we'll meet later. So the broad line region is not simply a static ring of clouds. It may be a dynamic exchange zone where gas orbits, rises, falls, and sometimes escapes. The physical conditions in the BLR are extreme, but not impossible to describe. The gas is dense compared with much of interstellar space. It is strongly ionized by the quasar's radiation. It sits close enough to the black hole that orbital times may be measured in months or years for some regions, rather than millions of years like stars far out in a galaxy. The light from the disk constantly changes the ionization state of the gas. Dust cannot survive in the innermost BLR because it is too hot and too strongly irradiated. Farther out, beyond a certain distance, dust can exist, and that dusty boundary may help define the outer edge of the broad line region. The BLR is therefore tucked between the blazing disk and the dusty surrounding structure, in a zone where gas can glow fiercely without becoming part of the cooler, dusty environment. There is a kind of order here, even if it is not tidy. At the very centre is the black hole. Around it lies the inner accretion disk and X-ray emitting corona. Outside that, or overlapping with parts of it depending on the model, is the broad line region of fast gas. Farther out is the dust that glows in infrared. Beyond that is the narrow line region, where gas moves more slowly and can extend over much larger scales. Jets, if present, emerge along the axis. Winds may flow from the disk. A line of sight cuts through this arrangement at one angle. What we call the quasar type depends on which parts are visible and which features dominate. Broadline quasars are the ones where that fast inner gas is on display. This also helps explain why broadline quasars often look so brilliant in optical and ultraviolet light. If we can see the broadline region, we are usually seeing relatively close to the central engine, without heavy obscuration blocking the view. The accretion disk's intense light reaches us more directly. The broadline gas is illuminated strongly enough to shine. The spectrum becomes rich with wide emission features. It is as if the quasar has opened the curtains around its centre, just enough for us to watch the gas race around the dark heart. Of course, the word watch is doing a lot of work there. We're not watching clouds circle in real time like birds around a tower. The distances are huge, the light is ancient, and the motions are inferred from spectra, but that does not make the picture less real. It only makes the method more elegant. A line width becomes a velocity becomes a clue to mass. A delay becomes a distance. A collection of distant points becomes a population of growing black holes across cosmic time. The broadline quasar is both an object and a technique for learning. For a calm bedtime image, you might imagine the broadline region as a restless ring of fireflies around a dark well, except the fireflies are clouds of ionized gas. The well is a supermassive black hole, and the whole scene would destroy any nearby garden furniture. The gas circles and stirs under gravity. The disk flashes and warms it. The gas replies in spectral lines. Some replies are broad because the gas is moving so quickly. Those widened replies cross the universe, enter our telescopes, and tell us that near the centre of that distant galaxy, matter is racing around one of nature's deepest gravitational wells. broad-line quasars are important because they give us a relatively direct look into the active nucleus. They show the fast gas. They help measure black hole mass. They reveal the structure of the inner regions. They connect quasar brightness to physical scale through reverberation mapping. They help astronomers trace black hole growth from the nearby universe to the earliest known quasars. They are not merely bright points. They are systems with measurable internal motion. Their light is not a single shout, but a layered message, with each line carrying information about the gas that made it. What happens when that fast inner region is hidden, blocked, or overwhelmed by another view? What kind of quasar do we see when the central engine is still powerful, but the broad-line gas is no longer fully visible to us? Not every quasar lets us look straight into its bright centre. Some of them are more private about the whole arrangement. The supermassive black hole may still be feeding, the accretion disk may still be shining with enormous power, gas may still be moving at high speed close to the centre, dust may still be heated until it glows in the infrared. But from our particular direction in space, the inner regions are partly hidden. The broad line region, that fast gas we have just been thinking about, is blocked from view by thick material around the nucleus. What reaches us most clearly are the narrower emission lines from gas farther out, beyond the dusty curtain. These are the narrow-line quasars in the Type 2 sense, and they show us that sometimes the most important part of a quasar is not what we see directly, but what something else is hiding from us. The name can be a little confusing, because astronomy has more than one object with narrow line in its description. There are narrow-line Seyfert-1 galaxies, which are a different kind of active galactic nucleus with their own specific properties. But here we are talking about luminous obscured quasars, often called Type 2 quasars. In these systems, the broad emission lines that would normally reveal fast gas near the black hole are weak, hidden, or absent from the direct spectrum. Instead, the visible spectrum is dominated by narrow emission lines from more distant gas. The central engine is still there. It is not switched off. It is simply being viewed through a different kind of cosmic architecture. To picture this, imagine a bright lamp inside a room with thick curtains around it. If the curtains are open, you see the bulb directly, and its light is sharp and obvious. If the curtains are closed, you may still see light leaking around the edges, glowing through the fabric, or reflecting off the walls outside the room. You know the lamp is there because the room is illuminated, but you cannot look directly at it. A narrow-line quasar works in a roughly similar way. Though the lamp is an accreting supermassive black hole, the curtains are dust and gas arranged around the nucleus, and the room is a galaxy. So, admittedly, it is not the kind of lamp you would want on your bedside table. The dust around an active galactic nucleus is often described as a torus, a thick donut-shaped structure around the central disk. This is a helpful starting image, though real dust around quasars is probably clumpy, uneven, and more complicated than a neat pastry in space. From some angles, our view looks down toward the accretion disk and the broad line region. From other angles, the dusty material blocks the centre. In the blocked view, the broad line gas is hidden because it lies close to the black hole, inside or behind the obscuring structure. The narrow line gas, however, is farther out. It can extend beyond the dust and still be visible. That is why narrow-line quasars can show strong narrow lines even when the broad lines are missing. This idea is part of what astronomers call the unified model of active galactic nuclei. The basic thought is that some different-looking active galaxies may be the same kind of engine seen from different directions. A Type 1 quasar gives us a more direct view of the central disk and broad line region. A Type 2 quasar gives us a more obscured view, where dust blocks the direct sightline to the inner engine. The black hole and accretion disk may be similar in both, but the view changes. As with so much in astronomy, perspective matters. The universe does not arrange distant quasars so they all face Earth politely. We see them from wherever we happen to be. The narrow lines come from gas moving more slowly than the gas in the broad line region. Slowly, of course, is a relative word here. The narrow line region can still involve gas moving at hundreds of kilometers per second, which would be a fairly brisk commute by human standards. But compared with the thousands of kilometers per second typical of broad-line gas close to the black hole, the lines are narrow. This gas sits farther from the central black hole, often on scales of hundreds or thousands of light-years. It is lit by radiation escaping from the quasar, and it responds by emitting light at specific wavelengths. Oxygen, hydrogen, nitrogen, neon, and other elements can leave strong marks in the spectrum. These narrow lines become the visible calling card of an obscured quasar. One of the most important narrow lines in many studies is the forbidden oxygen line, written as O3 at 5007 angstroms. The word forbidden sounds dramatic, as if oxygen has been caught breaking a rule in a quiet library. In physics, it means the transition is very unlikely under dense laboratory conditions, but in the thin gas of space, where atoms can wait long enough before collisions interrupt them, the line can appear strongly. O3 is especially useful because it traces ionized gas excited by the active nucleus. In Type II quasars, strong O3 emission can help reveal the presence of a powerful hidden engine, even when the bright central continuum is blocked. The dust that hides the broad-line region does not simply make the quasar disappear, it changes the way the quasar's energy escapes. Some of the central light is absorbed by dust grains, heating them. Those grains then re-emit energy in infrared wavelengths. This means a narrow-line quasar may look faint or obscured in visible light, but extremely bright in the infrared. Infrared telescopes are therefore very important for finding and understanding dusty quasars. They can reveal the warm glow of hidden power. The visible spectrum shows narrow lines. The infrared shows dust heated by the buried engine. X-rays, if they can get through or scatter into our line of sight, may reveal even more about the obscuring material. Each wavelength peeks through a different window. A real example of this kind of object is IRAS 09104+4109. It is a hyperluminous infrared galaxy containing a Type II quasar, and it sits at the center of a galaxy cluster. It is often discussed as a dust-enshrouded quasar because its central active nucleus is hidden behind heavy obscuration while the system shines strongly in infrared light. It is also interesting because it shows how complicated a quasar environment can be. The active nucleus, dust, cluster gas, radio structures, and star formation all belong to the same larger scene. IRA SO 9104+4109 is not just a simple buried light bulb. It is a quasar wrapped inside a galaxy, inside a cluster environment, with several kinds of matter responding to the energy from the center. In IRAS 09104+4109, observations in X-rays and other wavelengths have been used to study how much material blocks the nucleus. Astronomers have debated whether it is Compton thick or Compton thin, which refers to whether the obscuring gas is thick enough to strongly scatter even high-energy X-rays. That distinction matters because it tells us how deeply buried the quasar is. A Compton-thick object is extremely obscured, so much so that the direct X-ray emission is difficult to see. A Compton-thin object is still obscured, but not as deeply. The details are technical, but the story is simple enough. This is a powerful quasar whose central engine is not openly visible from our direction, and scientists have to reconstruct its nature through reflected light, infrared emission, narrow lines, and high-energy observations. Another famous example is IRASF 10214+4724. It is a gravitationally lensed, dust-obscured quasar at high redshift, meaning its light has been magnified by the gravity of an intervening object. Lensing helps us see it more clearly than we otherwise could, although it also complicates the interpretation because different regions of the source can be magnified by different amounts. IRASF 10214+472. 4 became famous as an extremely luminous infrared source, and studies have shown that it contains an obscured active nucleus, along with strong dust emission and narrow line properties. It is an excellent reminder that dusty quasars can be discovered not because they shine plainly in visible light, but because their hidden energy is reprocessed into infrared radiation and magnified by cosmic geometry. Gravitational lensing adds another layer to the story. When a massive galaxy or cluster lies between us and a distant quasar, its gravity bends the light, sometimes stretching the image into arcs or multiple images. This does not create the quasar's power, but it can amplify our view of it. In the case of IRAS, F10214 plus 4724, lensing made an already interesting dusty system appear extraordinarily bright. It also means astronomers must be careful. The lens may magnify the narrow-line region differently from the dusty torus, star-forming regions, or central active nucleus. If one part of the source is boosted more than another, the object can look unusual, not only because it is physically unusual, but because the universe has placed a gravitational magnifying glass in the way. Helpful, yes. Simple, absolutely not. These examples show that narrow-line quasars are not weak quasars. In fact, many are extremely luminous. The point is that the luminosity is hidden or redirected. The central engine pours out radiation, but dust and gas block the direct route to us. Some light escapes along polar directions, away from the dusty structure. Some is scattered into our view by electrons or dust above and below the nucleus. Some is absorbed and re-emitted in infrared. Some ionizes distant gas and creates narrow emission lines. The quasar becomes visible by its effects rather than by a direct view of its centre. It is like knowing a storm is behind a hill because the clouds above it are lit. The wind is moving and the rain is reaching your side of the valley. Polarized light can sometimes reveal the hidden broad-line region. This is one of the cleverest parts of the story. If light from the inner quasar scatters off material above or around the obscuring dust, it can become polarized, meaning the waves are oriented in a particular way. When astronomers use polarimetry, they can sometimes detect broad lines in the scattered light, even when those lines are not visible in the ordinary direct spectrum. This shows that the broad line region exists, but our direct view is blocked. The quasar has not lost its fast inner gas. We are simply seeing its reflection. It is a little like hearing someone's voice echo down a hallway when the door to the room is closed. The narrow line region itself can be large and beautiful in a scientific sense. Since it lies outside the central dusty structure, radiation from the quasar can ionize gas over broad areas. In some objects, narrow line emission extends far into the host galaxy. The gas may form cones or elongated structures if the quasar's radiation escapes more easily along certain directions. These ionization cones are another clue that the central engine is hidden in some directions but open in others. The dust blocks the equatorial view, while radiation escapes above and below, lighting gas like a flashlight beam through mist. Again, the flashlight is a supermassive black hole accretion disk, so this is not a peaceful camping image for too long, but it works. Because the central light is obscured, Type II quasars can be especially useful for studying their host galaxies. In ordinary bright quasars, the nucleus can overwhelm the starlight around it. The host galaxy becomes hard to see, like trying to notice a candle next to a welding torch. In Type II quasars, the central glare is partly blocked, so astronomers may have a better chance of observing the galaxy itself. That helps them study star formation, galaxy shape, mergers, outflows, and the relationship between black hole growth and galaxy evolution. The dust that hides the quasar can therefore become scientifically useful. It turns down the central glare just enough for the surroundings to be studied. This does not mean Type II quasars are easy. Dust creates its own problems. It absorbs visible and ultraviolet light. It reddens the spectrum. It re-emits in infrared. It can be arranged in clumps. The amount of obscuration may change with direction. Some sources may be deeply buried, while others are only moderately obscured. In some cases, the host galaxy itself adds dust, not just the nuclear torus. A quasar may be hidden by material close to the black hole and also by dusty star-forming regions farther out. When astronomers look at a narrow-line quasar, they are often untangling several overlapping layers of absorption, emission, scattering, and starlight. The object is not simply behind one curtain. It may be behind curtains, blinds, fogged glass, and someone standing in the doorway holding a very bright infrared lamp. Finding narrow-line quasars has required surveys across different wavelengths. Optical surveys can identify candidates by strong narrow high ionization emission lines and weak or absent broad lines. Infrared surveys can find dust-obscured sources whose energy emerges as heat radiation. X-ray surveys can reveal buried active nuclei, especially at higher energies that penetrate gas more effectively than visible light. Radio observations can sometimes identify active galaxies where dust does not block the radio emission. Each method finds a slightly different population. This matters because if astronomers only search in visible light for blue, unobscured quasars, they will miss many dusty ones. The universe's census would be incomplete, and cosmic history would look cleaner than it really was. That census is important because obscured quasars may represent a major stage in black hole growth. A young or strongly feeding quasar may be surrounded by gas and dust, especially after a galaxy merger or a period of intense star formation. The black hole grows while hidden. Over time, radiation, winds, and perhaps jets may clear some of the surrounding material, allowing the quasar to appear more directly as a bright blue Type 1 quasar. This evolutionary picture is not the only explanation, and orientation still matters greatly, but it may be part of the story. Some Type 2 quasars may be hidden mainly because of viewing angle. Others may be hidden because they are in a dusty phase of their development. The same observed class can include more than one physical situation. That is a useful caution. A narrow-line quasar is not always just a broad-line quasar turned sideways. Orientation is powerful, but not everything. The amount of dust, the structure of the host galaxy, the age of the quasar episode, the rate of accretion, the presence of winds, and the aftermath of mergers can all matter. The unified model gives us a strong framework, but real quasars add details. They do not always behave as if they are diagrams in a textbook. They behave like galaxies with histories. The narrow lines also help astronomers estimate the quasar's power when the direct continuum is hidden. Since the narrow line region is lit by the central engine, the strength of certain emission lines can serve as a rough proxy for the intrinsic luminosity. Infrared emission from heated dust can also give clues. X-ray emission, corrected for absorption when possible, adds another measure. None of these is perfect alone. Dust geometry, covering factor, gas density, metallicity, and viewing angle can all affect the signals, but together they help reconstruct the hidden engine. It is a scientific version of understanding a room by the light spilling under the door, the heat from the wall, and the echo of voices inside. In some narrow-line quasars, outflows are visible in the narrow-line gas. The emission lines may be shifted, widened, or shaped in ways that show gas moving outward across the host galaxy. This is important for feedback. Even when the inner broadline region is hidden, the quasar can still be affecting its surroundings. Ionized gas can be pushed outward, molecular gas may be disturbed, star formation may be regulated or rearranged. In luminous, obscured quasars, high-velocity ionized gas is often discussed as evidence that the quasar is influencing the host galaxy. The hidden nucleus may not be visible directly, but its impact can be spread across thousands of light years. There is something very human about how scientists study these objects. We are used to thinking that seeing directly is best. Open the curtain, look at the thing, and there is your answer. But narrow-line quasars teach the opposite lesson. Sometimes indirect evidence is richer. If the center were fully exposed, its glare might wash out the host galaxy. Because it is obscured, we can study the gas it illuminates, the dust it heats, the galaxy it lives in, and the ways its energy escapes. The blocked view is not just an obstacle, it is also a filter, and a filter can reveal structure that would otherwise be lost in brightness. The dust itself is not just a nuisance. Dust grains are tiny solid particles, often made of carbon-based and silicate materials mixed with gas in space. They absorb and scatter light, especially shorter wavelengths. That is why dusty objects can look redder. Blue and ultraviolet light are more strongly affected, while longer red and infrared wavelengths pass through or are re-emitted more easily. In quasars, dust near the nucleus can survive only beyond a certain distance, because too close to the accretion disk, the radiation is strong enough to sublimate it. The inner edge of the dusty region is therefore set partly by the quasar's luminosity. A brighter quasar can destroy dust farther out, pushing the dust survival boundary to larger distances. Even the dust has to negotiate with the central engine. This gives narrow-line quasars a layered temperature structure. The inner disk is extremely hot and bright in ultraviolet and optical light. The broad line region lies close in but hidden from certain directions. The dusty structure absorbs light and warms up, glowing in infrared. Farther out, cooler dust may emit at longer infrared wavelengths. Narrow-line gas, spread across larger distances, emits optical and ultraviolet lines depending on its ionization. X-rays may be absorbed, scattered, or reflected. The object is not one light source. It is a whole system of conversion where energy starts near the black hole and is transformed as it travels outward through gas and dust. IRAS, Q 9104 plus 4109, and IRAS F102, 14 plus 4724. Both show why infrared astronomy became so important for this field. Their infrared brightness tells us that something powerful is heating dust. In some systems, star formation also contributes strongly to infrared emission, because young stars heat dust in their birth clouds. So astronomers must separate the contribution from star formation and the active nucleus. This can be done through spectral features, energy distribution modelling, high-resolution images, X-ray observations, and emission line diagnostics. Again, nothing is perfectly simple. A dusty quasar can live in a star-forming galaxy, and both the stars and the black hole can heat dust. The challenge is to decide how much each contributes. For a slow mental image, picture a galaxy whose centre is wrapped in a thick, dusty ring or cocoon. Deep inside, the supermassive black hole feeds. The accretion disk shines, but much of that direct light cannot reach us. Above and below the dusty structure, radiation escapes in cones, striking gas farther out and making it glow in narrow lines. Dust closer in absorbs light and releases it as infrared warmth. If there are winds, they push gas outward. If there has been a merger, the galaxy may be disturbed and dusty on larger scales. From Earth, the object may not look like a typical bright blue quasar. It may look red, infrared luminous, line-dominated or heavily absorbed. But underneath the dust, the same kind of enormous engine is working. The narrow-line quasar is therefore a reminder that classification is not only about the engine, it is about the route light takes before it reaches us. Broad-line quasars show us the fast gas near the black hole because our view is relatively open. Narrow-line quasars show us the outer illuminated gas because the inner region is hidden. Both are real. Both reveal part of the active nucleus. Neither gives the whole picture alone. To understand quasars, astronomers need the direct view, the obscured view, the radio view, the infrared view, the X-ray view, and the patient willingness to compare them all. A quasar's colour is not just a colour, it is a clue. It tells us something about heat, dust, distance, viewing angle, and sometimes even the changing mood of the engine around a supermassive black hole. After looking at broad-line quasars, where fast gas near the centre is visible, and narrow-line quasars, where dust blocks that inner view, we can now step into one of the more slippery parts of the quasar family. Some quasars look blue because the hot inner light reaches us with relatively little obstruction. Some look red because dust has filtered and reddened the light before it escapes. And some quasars do something even stranger. They change their appearance over time, as if the central engine has switched faces. These are called changing-look quasars, and the name is unusually clear for astronomy. Many astronomical names sound as if they were assembled by a committee during a long meeting with cold coffee, but this one says almost exactly what it means. A changing-look quasar is a quasar whose spectrum changes dramatically enough that it appears to move from one active type to another. The broad emission lines may fade or vanish. The blue continuum from the accretion disk may dim. Later, in some cases, the broad lines may return. A quasar that once looked like a bright Type 1 object, with broad lines from fast gas near the black hole, may begin to look more like a dimmer Type 1.9 or Type 2 object, where those broad line features are weak or absent. It is not simply flickering like a candle in a draught. It is changing the way its inner engine presents itself to the universe. This is surprising because quasars are powered by structures that should not always change so quickly, at least not according to the simplest expectations. A supermassive black hole is enormous. The accretion disk around it can stretch across light days, light weeks, or more. The broadline region may sit still farther out. In older, simpler pictures, the differences between broadline and narrowline objects were often explained mainly by viewing angle and dust. If you saw the centre directly, you saw broad lines. If dust blocked the view, you saw narrow lines. That idea is still very useful, but changing-look quasars complicate it. They show that in some cases the quasar itself may actually brighten or fade, enough that the broadline region responds. The face changes not because Earth has moved to a new viewing angle, which would be inconvenient and also not happening, but because the central light source has changed. The broadline gas depends on the bright inner continuum. It is lit by energetic radiation from the accretion disk and nearby hot regions. If that radiation weakens greatly, the gas may no longer produce the same strong broad emission lines. The gas can still be there, orbiting near the black hole, but without enough ionizing light its spectral signature fades. This is an important point. When broad lines disappear in a changing-look quasar, it does not necessarily mean the gas itself has physically flown away in a few years. It may mean the lamp that makes the gas glow has dimmed. The room is still furnished, but someone has turned down the light. One famous example is DSJ 01595 7.64 plus 00331 0.5, often shortened in discussion to J, 0159 plus 0033. It was identified as a changing-look quasar after observations showed that it had shifted from a Type 1 quasar state to a Type 1.9 state between 2000 and 2010. In its brighter state, it showed the broadline features expected from a quasar with a visible broadline region. Later, its continuum dimmed and the broad hydrogen emission weakened dramatically. This was one of the key discoveries that pushed changing-look quasars into wider attention. It showed that a luminous quasar could undergo a major spectral transition on human observable timescales, not millions of years, not even thousands, a decade. That is practically impatient by black hole standards. At first, one might suspect dust. Perhaps a cloud moved in front of the quasar and blocked the broadline region. That would be a tidy explanation, and tidy explanations are always tempting. But for J0159 plus 0033, the evidence pointed more toward intrinsic dimming of the central engine rather than simple obscuration. The optical and X-ray changes did not behave like a straightforward dust curtain passing across our view. Instead, the quasar seemed to have reduced its output, which lowered the supply of ionizing photons available to light up the nearby gas. In other words, the central engine itself became less luminous. It was not merely hiding, it was fading. Another well-known example is SDSSJ 101152.98 plus 5442 06.4, often called J1011 plus 5442. This object became known as a changing-look quasar when repeat observations showed that its broad emission lines had largely disappeared as the source faded. Later work has found signs that it may be returning toward a Type 1 state, with broad lines becoming visible again. That makes it especially valuable, because a quasar that changes one way and then begins to change back gives astronomers a better chance to study the mechanism. A one-time fading event is interesting. A cycle, even an incomplete one, is a stronger clue that the central accretion process itself may be shifting. These objects are important because they let astronomers watch black hole feeding change in real time, or at least real time by astronomical standards. Usually when we study galaxies and black holes, we see snapshots. One galaxy is active, another is quiet. One quasar is bright, another is obscured. We infer evolution by comparing many objects at different stages, a little like trying to understand human aging by walking through a train station and looking at strangers of different ages. Changing look quasars give us something rarer. They let us watch the same object change, the same galaxy, the same central black hole, the same host environment, but a different state of activity. That is a gift, scientifically speaking, though perhaps a rather stressful one for anyone trying to keep the classification neat. What causes the change? The leading explanations often involve changes in the accretion flow, meaning the rate or structure of matter feeding the black hole changes enough to alter the emitted light. If less material reaches the hottest inner regions, the disk may dim. If the disk state changes, the high-energy radiation that ionizes the broadline gas may decline. The broadlines fade. If the accretion flow strengthens again, the broadline region can brighten. There may also be cases where obscuration, tidal disruption events, disk instabilities, or other processes play roles, but many changing look quasars seems difficult to explain by dust alone. The basic mystery is not that quasars vary, they do. The mystery is that some change so much, so quickly, and so completely in spectral appearance. The timescale is the real troublemaker. In a simple accretion disk, some changes should move slowly, especially if they involve material travelling inward from large disk radii. Yet changing look quasars can shift over years. That forces theorists to think carefully about disk physics, thermal changes, instabilities, magnetic processes, and how radiation from the inner disk controls the broadline region. This is one of those places where the universe says, very politely, that the textbook diagram was a good start but not the whole story. Changing look behaviour also makes us rethink the meaning of quasar types. If a quasar can move from a broadline appearance to a weak broadline appearance, then some classifications are not permanent identities. They are states. A quasar can be in one state when one survey observes it, and another state years later. That matters for large catalogues. It also matters for how astronomers estimate quasar lifetimes, duty cycles, and black hole growth. A quasar may not simply turn on for millions of years and then turn off smoothly. It may flicker, dim, brighten, pause, and restart in ways that are still being mapped. Feeding a black hole may be less like opening a steady tap and more like dealing with old plumbing in a large house. Sometimes pressure drops, sometimes it returns, sometimes something rattles in the walls. Now, colour enters the story because the central continuum of a quasar is usually blue when it is seen clearly. The accretion disk is hot, and hot disks emit strongly an ultraviolet and optical blue light. A typical unobscured Type 1 quasar often appears blue in optical surveys, especially compared with ordinary galaxies, because the bright disk dominates the light. Blue quasars are therefore often the ones where our view of the central engine is relatively open. We see the hot accretion disk, broad emission lines, and less dust reddening along the way. The blue colour does not mean the quasar is calm. It means the hottest light has a clearer route to us. A blue quasar can be thought of as a central engine with the curtains pulled back. The disk shines. The broadline gas glows. The ultraviolet light, stretched by redshift depending on distance, reaches our telescopes in the wavelengths we can observe. In many surveys, these blue colours helped astronomers find quasars efficiently, because they stood apart from the colours of most stars and galaxies. A quasar might look like a point of light, but its colours and spectrum reveal that it is not a star. It is a distant galactic nucleus with a black hole engine. This is another reminder that astronomy often starts with colour differences so small that a casual eye would miss them, then ends with black holes billions of light years away. A good colour selection can be a very quiet doorway to a very loud object. Red quasars are more complicated. A quasar can look red for several reasons. Dust is one of the main ones. Dust grains absorb and scatter shorter blue wavelengths more effectively than longer red and infrared wavelengths. This is similar to the way dust in our own galaxy can make stars look redder than they really are. If a quasar's light passes through dust in its host galaxy, or near the active nucleus, the blue and ultraviolet light can be suppressed, while redder light comes through more easily. The result is a quasar that is intrinsically bright and hot, but appears redder to us. The engine may be blue at the source, but the path has changed the colour. This matters because red quasars may reveal a dusty stage of quasar evolution. In one possible picture, a quasar begins its bright growth while still surrounded by gas and dust, perhaps after a galaxy merger has driven material inward. The black hole feeds heavily. Star formation may be active. Dust blocks and reddens the central light. As the quasar grows more powerful, radiation and winds may clear some of that dust and gas, eventually revealing a more typical blue quasar. In this view, red quasars are not simply blue quasars seen through a little dust by accident. They may be transitional objects, caught during a phase when the central engine is emerging from a dusty environment. The picture is attractive, though real quasars may not all follow one simple path. There are also other reasons a quasar might look red. Its continuum may be intrinsically redder because of the accretion disk properties. Hot dust emission can contribute in the near-infrared. Viewing angle may play a role if the line of sight passes through the outer parts of the dusty structure, but not enough material to hide the quasar completely. At high redshift, cosmic expansion shifts ultraviolet light into redder observed wavelengths, and absorption by gas between galaxies can remove parts of the blue spectrum. So when astronomers say red quasar, they must be careful. Redness is a clue, not an answer. It says, something has happened to this light. It does not immediately say what. To decide what makes red quasars red, astronomers compare spectra across optical and infrared wavelengths. Infrared observations are especially helpful because they can look through dust more effectively and sample emission lines less affected by extinction. Line ratios can reveal how much dust lies along the path. If certain hydrogen lines are much stronger or weaker than expected compared with others, that can indicate reddening by dust. Studies of red quasars have found evidence that dust extinction is often a major cause of their colour. That supports the idea that many red quasars are dust-reddened, possibly connected to active growth phases in dusty host galaxies. The difference between red and blue quasars therefore tells us about both the engine and its surroundings. Blue quasars often show a clearer, more direct view of the hot disk. Red quasars often reveal that dust is present along the line of sight, perhaps because the quasar is embedded in a dusty galaxy or viewed through part of the nuclear dust structure. A blue quasar says, "Here is the furnace." A red quasar says, "Here is the furnace through smoke." Both are quasars, both may be powered by similar black hole accretion, but their colours tell us that the light has taken different paths through different environments. Changing look quasars add a time dimension to this colour story. When the accretion disk brightens, the object may become bluer because the hot disk contributes more strongly. When the disk fades, the host galaxy may become more visible, and the overall colour can change. Broad lines may weaken as the ionizing continuum drops. A quasar can therefore change not only its spectral type, but also its colour and the balance of light between nucleus and host galaxy. In the bright state, the quasar can overwhelm its host. In the dim state, the galaxy around it can come forward, like scenery becoming visible after a spotlight is lowered. This is one of the useful side effects of changing look quasars, When the nucleus fades, astronomers can study the host galaxy more easily. The bright central point no longer washes out everything around it as strongly. This gives researchers a chance to ask what kind of galaxy hosts a changing-look quasar. Is it disturbed? Has it recently merged? Is it forming stars? Does it have enough gas to feed the black hole again? The fading is not merely a loss of light. It opens a window onto the surroundings. The quasar turns down, and the galaxy becomes easier to hear. There is something almost personal about changing-look quasars, though of course the quasar itself has no intentions. It is not deciding to appear as one type in one decade and another type in the next. It is matter, radiation, gravity, and magnetism behaving according to physics. But from our distant viewpoint, the effect is striking. A spectrum taken years apart can look like a different object. Lines that once stood broad and bright may fade into almost nothing. Later, they may begin to return. It gives the impression of a cosmic engine breathing, though the real cause is likely changing accretion and radiation rather than anything so gentle. Still, for a bedtime science journey, the image can rest there for a moment. A black hole engine brightens, dims, and brightens again, while its surrounding gas answers in light. The colours of quasars also remind us that no observation is pure. Light is shaped by the source, but also by everything between the source and the observer. A blue quasar may be blue because the disk is hot and visible. A red quasar may be red because dust has filtered its light. A distant quasar may appear redder because the universe expanded while the light travelled. Gas between galaxies can absorb ultraviolet light. The host galaxy can add starlight. The telescope observes the final mixture, and astronomers work backward. It is like receiving a cup of tea and trying to determine not only which leaves were used, but also the water temperature, the teapot material, whether someone added milk, and how long it sat on the counter. Possible, with enough evidence, but not something one should pretend is simple. The idea of quasar colour has practical importance for surveys. Many early quasar searches relied on the unusual blue colours of quasars. That worked well for finding unobscured blue quasars, but it could miss dust-reddened quasars. Infrared surveys helped reveal more red quasars, because dust-hidden objects often emit strongly at longer wavelengths. Radio and X-ray surveys can also find quasars whose optical colours are less obvious. Every selection method has biases. A blue search finds blue objects. An infrared search finds dusty, warm ones. A radio search finds jet-related sources. To understand the full quasar population, astronomers need several methods, because the universe does not promise that all its black holes will show up in the same colour jacket. In this sense, red quasars are important, not only because they are interesting individually, but because they correct the census. If many quasars are dust-reddened or obscured, then a survey that finds only blue quasars will underestimate how many black holes are growing. That affects our understanding of cosmic black hole growth, galaxy evolution, and the history of radiation in the universe. Dust can hide activity, and hidden activity still matters. A black hole does not stop growing just because our optical telescope has trouble seeing it. There is also a connection with winds. Some red quasars show strong outflow signatures, suggesting that dusty or transitional quasars may be actively clearing material from their surroundings. That fits the idea of an emerging quasar phase, where the central engine is powerful enough to blow gas outward, but still partly wrapped in dust. Blue quasars may represent a later or cleaner view, after more of the obscuring material has been removed, though again orientation and individual history complicate the story. Red and blue are not moral categories. One is not old and one young in every case. They are observational clues that must be interpreted with care. Changing-look quasars also warn us that colour and type can change with time. Suppose a survey observes a quasar when it is bright and blue. Years later, another survey observes it dimmer and redder, with weaker broad lines. Without repeat observations, those might look like different kinds of objects in a population study. With repeat observations, they become the same object in different states. This is why time domain astronomy has become so important. By watching the sky repeatedly, astronomers find not only new objects but changing objects. The universe is not a still photograph. It is a long exposure filled with flickers. The technology behind this is quiet but powerful. Surveys like the Sloan Digital Sky Survey, Pan-STARRS, ZTF, WISE and others have given astronomers repeated measurements of large areas of the sky. Spectroscopic follow-up then shows whether colour and brightness changes are accompanied by changes in emission lines. A light curve shows when the object brightened or faded. A spectrum shows what happened to the gas. Infrared data can show dust responding more slowly to changes in the central light, because dust lies farther out and reprocesses the radiation. X-rays can reveal changes in the inner engine. Each wavelength responds from a different region, so the changing quasar becomes a layered time experiment. If the optical light dims first, and the infrared follows later, that delay can suggest dust being heated by the central source and then cooling after the source fades. If broad lines fade after the continuum drops, the broad line region is responding to the reduced ionizing radiation. If X-rays change along with optical light, the inner accretion flow may be changing. These timing relationships help distinguish between dust clouds crossing the line of sight and intrinsic changes in the central engine. Dust crossing might block optical light while leaving some other signals less affected depending on geometry. Intrinsic dimming should change the energy supply itself. The details are subtle, but the principle is gentle enough. Different parts of the quasar answer at different times, and those answers reveal the structure. A changing look quasar is therefore not just a curiosity, it is a diagnostic tool. It allows astronomers to test how the accretion disk, broadline region, dusty torus, and host galaxy are connected. It can show how quickly a broadline region responds. It can reveal whether the dust is close or far. It can help determine whether the change is caused by obscuration or by a change in accretion. The quasar's shifting face becomes a scientific experiment arranged by nature, which is considerate, though nature did place it hundreds of millions or billions of light years away, so there are limits to its helpfulness. As we hold all of this together, the family resemblance becomes clearer. Narrow-line quasars showed us what happens when dust hides the inner region. Broadline quasars showed us the fast gas when the inner region is visible. Red quasars show us how dust and environment can reshape the colour of a quasar without necessarily removing its power. Blue quasars show us the hot disk more directly. Changing look quasars show us that some of these appearances can shift over years, because the engine itself can brighten or fade. The categories are not rigid walls, they are windows into a changing system. For a calm, final image before moving onward, picture a distant galaxy with a bright centre that does not always keep the same expression. In one era of observation, the central disk shines strongly, blue light pouring out, broad lines glowing from fast gas near the black hole. In another, the disk has dimmed, the broad lines have weakened and the host galaxy becomes more visible. Somewhere else, dust reddens the light, turning a hot blue engine into a warmer-looking red quasar. In another object, the view is cleaner, and the blue continuum dominates. The black hole itself remains dark, but everything around it changes how the darkness is revealed. Colours, in the end, are not just decoration on quasar light, they are records of the journey. Blue can mean a clearer view of heat, red can mean dust, distance, or a different stage of growth. A changing look can mean the engine has altered its output, and the surrounding gas has responded. When astronomers classify quasars by colour or spectral state, they are not simply sorting lights in the sky. They are reading the conditions around supermassive black holes and watching how those conditions evolve. There are some quasars that do not merely shine across the universe. They aim, not intentionally of course. A quasar does not wake up one morning, adjust its cosmic posture, and decide to point a beam toward a small planet orbiting an ordinary yellow star. But from our point of view, it can look almost that way. In a blazar, one of the relativistic jets from an active galactic nucleus is pointed nearly along our line of sight. The jet is not just present, as it is in a radio-loud quasar. It is aimed so close to us that its light becomes boosted, intensified, and made restless by the effects of special relativity. The result is one of the most dramatic appearances in the quasar family, a bright, rapidly variable object whose energy seems to surge from radio waves through visible light, X-rays, and gamma rays. This is where perspective becomes almost everything. The central engine is still the familiar one, a supermassive black hole, an accretion disk, hot gas, magnetic fields, and in this case, powerful jets. But because the jet is angled close to Earth, we do not see the system in the same way we would from the side. We are looking nearly down the beam. It is a little like standing in front of a flashlight instead of watching it from across the room. The flashlight has not become more powerful in itself, but from your position, it appears much brighter. Now replace the flashlight with plasma moving at nearly the speed of light. Replace the room with intergalactic space, and replace the mild inconvenience of being dazzled with the detection of violent variability from billions of light years away. Astronomy does enjoy taking simple comparisons and making them wildly unsafe. The key effect is called relativistic beaming. When material in a jet moves close to the speed of light toward us, the radiation from that material is concentrated in the forward direction. The light is boosted, the apparent brightness increases, and changes in the jet can appear compressed in time. That means a blazar may brighten or fade very quickly, sometimes over days, hours, or even shorter timescales depending on the wavelength and the event. This variability tells astronomers that the emitting region can be extremely compact. If something changes quickly, the region responsible cannot be too large, because information cannot coordinate a change faster than light can cross it. A sudden flare becomes a size clue. The jet flickers, and the flicker tells us that part of the action is happening in a very small region of an enormous system. This is one reason blazars feel so alive in the data. Many astronomical objects change slowly by human standards. Stars evolve over millions or billions of years. Galaxies merge over hundreds of millions of years. Even ordinary quasar activity can be steady enough that it feels almost fixed from one night to the next. But blazars can flare dramatically. Their brightness can jump, their polarization can swing. Their gamma ray output can rise suddenly, as if a hidden part of the jet has been stirred. To astronomers, these changes are not just dramatic, they are diagnostic. They reveal how particles are accelerated, how magnetic fields are arranged, where radiation is produced, and how energy travels from the black hole environment into the jet. A blazar is usually divided into two major observational groups, BL-lac objects and flat-spectrum radio quasars. BL-lac objects, named after B.L. Lacerté, tend to have weak or nearly absent emission lines in their spectra, because the jet's bright continuum can overwhelm the line emission, or because the line-producing environment is less prominent. Flat-spectrum radio quasars, often called FSRQs, show stronger broad emission lines, meaning that the quasar-like broadline region is clearly present. OVV quasars, or optically violently variable quasars, are historically connected with this family. They are broadline quasars that show strong, rapid optical variability and other blazar-like properties. In modern terms, many OVV quasars are closely related to flat-spectrum radio quasars. The categories overlap because, once again, nature made the objects first and let humans argue about the labels afterward. The phrase optically violently variable sounds almost theatrical, as if the quasar has been asked politely to calm down and has refused. The optical part means the variability is seen in visible light. Violently variable means the brightness can change strongly and rapidly. Quasar means the object still has the broad emission lines and luminous active nucleus of a quasar. Put together, An OVV quasar is a jet-dominated, highly variable quasar where the beam is playing a major role in what we see. It is not only the accretion disk shining. It is the jet adding a restless, boosted contribution, sometimes so strong that it can make the object behave more like a BL-lac object during bright states. One famous example of a blazar-like quasar is 3C279. It is a well-studied flat-spectrum radio quasar, famous for strong variability across many wavelengths, including gamma rays. Its jet is aimed close enough to our line of sight that relativistic beaming makes it appear extremely bright. 3C279 has been watched by radio telescopes, optical observatories, X-ray satellites, and gamma-ray missions, because no single wavelength tells the whole story. In gamma rays, it can flare with astonishing strength. In radio, very long baseline interferometry can trace compact jet structures and apparent motion that seems faster than light. That apparent faster-than-light motion is not a violation of relativity. It is a projection effect caused by material moving close to the speed of light at a small angle to our line of sight. The jet is not actually outrunning light, which is good, because physics would have had a very awkward meeting otherwise. Apparent superluminal motion is one of the classic signs of relativistic jets. Imagine a blob of plasma moving almost directly toward us, but slightly across our line of sight. Because it is moving so fast and nearly toward us, the light it emits at later times has less distance to travel to reach us. This can make its sideways motion across the sky appear faster than light, even though the blob itself remains below light speed. It is geometry and timing conspiring to look impossible. Blazars are full of this kind of trick. They do not break the rules. They show us the rules from a very inconvenient angle. Another famous blazar is BL Lacertae itself, the object that gave BL-lac objects their name. When it was first catalogued, it was thought to be a variable star, because it looked like a point of light and changed in brightness. Later, astronomers realized it was not a star in our galaxy, but the active nucleus of a distant galaxy with a jet aimed toward us. That history is a lovely reminder of how astronomy often progresses. Something looks ordinary, then it behaves oddly, then the odd behavior becomes a doorway to a much larger truth. BL Lacertae went from suspicious variable star to prototype of a whole class of jet-dominated active galactic nuclei. Not a bad career change for a point of light. OJ287 is another well-known blazar, famous for its long record of optical variability and for the possibility that it contains a binary supermassive black hole system. Its brightness has shown repeated outbursts over many decades, and those outbursts have inspired models involving one black hole disturbing the accretion disk of another. The details are still studied and debated, but OJ287 is valuable because it has been monitored for such a long time. A long-light curve is like a diary kept by the universe, though the handwriting is made of flares, dips, and uneven sampling. In a blazar, those changes may arise from the jet, the disk, shocks, magnetic activity, or interactions in the central system. The more complete the record, the better astronomers can separate patterns from chance. The jet in a blazar is not a smooth pipe of glowing material. It is structured. It may contain knots, shocks, turbulent regions, and zones where particles are accelerated to extremely high energies. Magnetic fields thread the jet and can influence both the motion of particles and the polarization of light. Polarization is especially useful because it tells astronomers about the orientation and order of magnetic fields in the emitting region. If the polarization angle changes, that may suggest a rotating magnetic structure, a shock moving through the jet, or a change in the dominant emission zone. The light is not only bright, it is oriented, and that orientation carries information. The radiation from blazars is often described with two broad humps in its spectral energy distribution. The lower energy hump is usually produced by synchrotron radiation, where high-energy electrons spiral through magnetic fields. This can cover radio through optical or even X-ray wavelengths, depending on the kind of blazar. The higher energy hump is often explained by inverse Compton scattering, where energetic electrons boost lower energy photons to X-ray or gamma-ray energies. Those seed photons may come from the jet's own synchrotron light, from the accretion disk, from the broadline region, or from dusty regions around the nucleus, depending on the object. The details can become complicated, but the broad picture is manageable. Electrons in the jet are moving fast, magnetic fields make them radiate, and those same electrons can also kick photons up to higher energies. This is why blazars are among the brightest gamma-ray sources in the sky. Gamma rays come from some of the most energetic processes we can observe, and blazar jets are natural places to make them. The Fermi Gamma Ray Space Telescope has found and monitored many blazars, turning the high-energy sky into a changing map of jet activity. When a blazar flares in gamma rays, astronomers often coordinate observations across the world and in space, trying to catch the event in radio, optical, X-rays, and gamma rays at the same time. This multi-wavelength approach is essential because a flare may begin in one part of the spectrum and appear later in another. The timing can reveal where the flare occurred and how energy moved through the jet. A blazar flare is not simply a light switch being flipped. It may involve a shock travelling down the jet, particles being accelerated, magnetic energy being released, or a new component emerging from the radio core. Some models involve magnetic reconnection, where magnetic field lines rearrange and release energy, somewhat like processes that power solar flares, but scaled into a far more extreme environment. Others involve shocks caused by faster material catching slower material in the jet. The real answer may vary from flare to flare and object to object. Blazars are not kind enough to use only one mechanism, they prefer a menu. OVVV quasars fit especially well into this idea of restless beamed light. Because they have broad emission lines, we know that the quasar's surrounding line-emitting gas is present and illuminated. Because they vary strongly in optical light, we know the jet is contributing significantly to what we see. During a high state, the jet continuum can become so bright that it washes out or weakens the apparent strength of the emission lines, making the object look more BL or LAC-like. During a lower state, the broad lines may become easier to see again. This means the classification can shift depending on the jet brightness. The object is not necessarily changing its entire structure. The balance of light is changing. If the jet turns up the volume, the spectral lines seem quieter by comparison. This is an important subtlety. In broadline quasars, the emission lines are clear because the disk and broadline region are visible. In OVV quasars, the broadlines may still be there, but the beamed continuum from the jet can dominate the scene. The equivalent width of the lines, a measure of line strength compared with the surrounding continuum, can decrease when the jet brightens. So an object can appear more line poor during a flare, not because the gas vanished, but because the continuum became overwhelming. It is like trying to hear someone speaking softly while a motorbike passes by. The voice is still there. The jet is just being rude. The viewing angle also affects time itself as we observe it. Relativistic motion compresses the apparent timescales. Events in the jet can appear to unfold faster because the emitting material is moving nearly toward us. A region that would seem slower from the side can look rapid from our viewpoint. This makes blazars excellent laboratories for extreme physics because they allow us to see compact, high-energy processes amplified by geometry. They also make interpretation challenging. Brightness is boosted, timescales are shortened. One side of the jet dominates. The other side may be nearly invisible. Everything we observe has been filtered through the fact that we are looking almost straight into the beam. That beam can also make the host galaxy difficult to see. In many blazars, the jet continuum is so strong that it overwhelms starlight from the galaxy and emission from other regions. The host is often an elliptical galaxy, especially for BL-lac objects, but measuring it can require careful imaging when the nucleus is not too bright. Again, the same theme returns. The brightest part can hide the context. In narrow-line quasars, dust blocks the centre and helps reveal the host. In blazars, the beamed jet can flood the view and bury the surroundings in light. Astronomy is often the art of subtracting glare. There is also a deep connection between blazars and radio-loud quasars. A blazar is essentially a radio-loud active nucleus viewed close to the jet axis. If the same object were viewed from the side, it might appear as a radio galaxy or radio-loud quasar with extended jets and lobes. From our angle, the compact core dominates. The extended structures may still exist, but the beamed core is so bright that it becomes the main feature. This is why blazars are central to unified models of active galaxies. They show how one physical engine can look dramatically different depending on orientation. The jet itself may carry energy far from the black hole before releasing it. In radio images, jets can show components moving outward over time. These components may be shocks or denser plasma knots. Tracking them helps astronomers estimate speeds, angles, and the energy flow. Very long baseline interferometry is especially important here because it can resolve tiny angular scales. With networks of radio telescopes spread across Earth, astronomers can watch structural changes in jets that are otherwise much too distant to image in ordinary detail. It is a strange form of watching, not seeing the jet as a continuous movie in visible light, but measuring radio structures over years and building a record of motion near a black hole, billions of light years away. Blazars are also important in multi-messenger astronomy. Some have been discussed as possible sources of high-energy neutrinos, tiny, nearly massless particles that travel through the universe with little interaction. When a neutrino is detected from roughly the same direction and time as a blazar flare, astronomers become very interested, because it may indicate that protons or heavier particles are being accelerated in the jet, not just electrons. This is a developing field, and individual associations must be treated carefully, but the possibility is exciting. A blazar jet may send not only light, but particles across cosmic distances. It may be one of the universe's natural particle accelerators, far larger and less tidy than anything built on Earth. For all this intensity, a blazar still begins with accretion. Without matter feeding the black hole, and without magnetic fields shaped by the disk and central rotation, the jet would not have its power source. The beam can dominate what we see, but the engine behind it remains the black hole accretion system. This is easy to forget because the jet is so visually and observationally dramatic. It points, flares, varies, polarizes, and sometimes floods the spectrum. But behind the beam lies the same deep arrangement we have followed from the beginning. Gravity pulling matter inward, matter heating and shining, magnetic fields organizing energy, and the galaxy's central black hole acting as the anchor. There is a useful difference between the two main blazar groups. BL-LAC objects often have weak emission lines and can have spectra, dominated by non-thermal jet radiation. Flat-spectrum radio quasars have stronger emission lines and often more luminous accretion disks and external photon fields around the nucleus. This means FSRQs can produce gamma rays through interactions between jet electrons and photons from outside the jet, such as light from the broadline region or dusty torus. BL-LACs, with weaker external fields, may rely more on photons produced inside the jet itself. That is the simplified version, and real objects can blur the categories, but it helps explain why their spectral energy distributions and variability can differ. The word non-thermal is worth pausing over. In a hot stove or a star's photosphere, much of the light is thermal, related to temperature. In a blazar jet, much of the radiation is non-thermal, produced by high-energy particles interacting with magnetic fields or photons. This gives the spectrum a different shape and allows emission across a huge range of energies. The jet is not glowing simply because it is hot in the ordinary way. It is radiating because particles are being accelerated to extreme energies and are losing energy through physical processes that leave broad, powerful signatures. A blazar is less like a furnace and more like a cosmic accelerator aimed in our direction. The variability can be so strong that blazars are monitored by amateur and professional astronomers alike in optical light. Some objects brighten enough to be followed with modest telescopes. This long-term monitoring matters because flares can be unpredictable. A professional observatory cannot watch every blazar every night in every wavelength, so networks of observers contribute valuable data. The universe changes whether or not the largest telescope is looking. A small telescope in a backyard can sometimes help catch the rise or fall of a distant jet. There is something quietly wonderful about that. A person under a night sky, perhaps with cold hands and a thermos nearby, measuring the flicker of a black hole beam from billions of light years away. The danger of the phrase aimed at us is that it can sound threatening. It is natural to wonder whether a blazar jet pointed at Earth could harm us. The answer, for known blazars, is no in any practical sense. They are extremely far away. Their radiation reaches us as detectable signals, not as a dangerous blast. If a powerful relativistic jet were nearby and aimed directly at a planet, that would be a very different conversation, and not one for a relaxing evening. But the blazars we study are safely distant. Their beams are violent in their own neighbourhoods and valuable to us as information. From here, they are cosmic messengers, not hazards. The reason they are so valuable is that they magnify the physics of jets. Because the emission is boosted, we can study processes that might otherwise be too faint. We can watch rapid changes, measure polarization swings, compare gamma-ray flares with radio knots, and test models of particle acceleration. Blazars are messy, yes, but they are also generous. They bring extreme jet physics almost directly to our telescopes. It is as if the universe has taken one of its most powerful laboratories and tilted it toward us, which is helpful, if a little bright. OVV quasars remind us that the boundary between quasar types can depend on what part of the object is currently dominating the light. When the jet is subdued, broad quasar lines and disk emission may be easier to recognize. When the jet flares, the continuum can rise sharply, polarization may increase, and the object may look more BL-like. In this way, OVV quasars sit at an intersection, clearly quasar-like because of their broad lines, clearly blazar-like because of their beamed variability. They are not a separate engine as much as a state of viewing and dominance, where the jet becomes the loudest voice in the room. If you picture the quasar family as a set of views around the same central structure, blazars occupy the line of sight looking down the jet. Radio galaxies may be the side view, with big lobes spread across space. Radio-loud quasars may be an angled view, where the bright nucleus and jet are both apparent. OVV quasars and flat-spectrum radio quasars bring us closer to the beam. BL-lac objects take the jet dominance even further, with weak lines and strong non-thermal emission. It is a family arranged not only by physical differences, but by angle. We are not just classifying objects, we are classifying our view of them. Some quasars do not only shine outward, they breathe outward. They push gas away from the edge of their brightest regions, sending material racing from the neighbourhood of the supermassive black hole into the larger galaxy beyond. This is where broad absorption line quasars, or BAL quasars, become so important. They show us not just the light made by a feeding black hole, but the shadow of gas moving in front of that light. Their spectra carry dark, wide troughs, where outflowing material has absorbed particular wavelengths before the light could continue on its long journey toward us. In a broadline quasar, fast gas announces itself by glowing. In a BAL quasar, fast gas announces itself by taking light away. That may sound like a small difference, but it changes the whole feeling of the object. Emission lines are like lamps turned on by gas. Absorption lines are like fingerprints pressed into a beam of light. When the bright accretion disk shines through a wind, Atoms and ions in that wind absorb specific wavelengths. Since the wind is moving toward us relative to the quasar's central source, those absorption features are shifted toward bluer wavelengths, and because the outflow contains gas moving over a wide range of speeds, the absorption is not a narrow little notch. It becomes broad, sometimes stretching across thousands or even tens of thousands of kilometers per second in velocity space. The spectrum looks as though a dark bite has been taken out of one side of an emission line. This is why the word broad matters in broad absorption line quasar. The broadness tells us that the absorbing gas is not sitting still. It is moving quickly, and not all at one single speed. Some parts of the wind may be slower, some may be faster, some may lie closer to the disk, some may be farther out. Together, they create a wide absorption trough, a long shaded region in the spectrum where light has been removed. The result is a direct sign of outflow. Matter is not merely orbiting the black hole, it is leaving the central region. A BAL quasar is usually still powered by the same central arrangement we have followed all along. There is a supermassive black hole in a galaxy's centre. Around it lies a hot accretion disk. The disk produces intense ultraviolet and optical light, with X-rays coming from a compact, hot corona closer in. Gas clouds and streams nearby make broad emission lines. Dust farther out absorbs and re-radiates energy in infrared light. But in a BAL quasar, a particular line of sight passes through a strong wind. The wind lies between us and the bright source. That wind is the difference. It filters the quasar's light before the light escapes into intergalactic space. A simple way to picture it is to imagine looking at a bright lamp through fast-moving smoke. The lamp is still there. It may still be painfully bright if you could see it directly. But the smoke absorbs and scatters some of the light, and because the smoke is rushing toward you, the pattern of missing light is shifted. Of course, actual BAL winds are not smoke in a room. They are ionized gas moving at speeds that can reach a significant fraction of the speed of light. The lamp is an accretion disk around a black hole. The room is the central region of a galaxy. The smoke has read several advanced papers in plasma physics and is behaving accordingly. The classic BAL features often appear in ultraviolet lines, especially from highly ionized elements such as carbon, silicon, and nitrogen. One of the most famous is the carbon-4 line, often written C4, which comes from carbon atoms that have lost 3 electrons. In many BAL quasars, the C4 region of the spectrum shows a broad absorption trough blue shifted from the emission line. That tells us carbon-rich, highly ionized gas is flowing outward. Other absorption can appear in lines like Si4, N5, Al3, Mg2, or even ion transitions in special cases. These different ions help astronomers classify the BAL quasar and learn about the ionization state, density and structure of the wind. There are several major BAL families. High BAL quasars, or high ionization BAL quasars, show absorption from high ionization lines such as C4 and Si4. Low BAL quasars, or low ionization BAL quasars, also show lower ionization absorption such as Mg2 or Al3. FeLO-BAL quasars are a rarer and more heavily absorbed group with broad absorption from excited ion transitions. Those names may look like someone dropped a handful of letters into a telescope logbook, but they carry useful information. High ionization absorption tells us about one kind of wind. Low ionization and ion absorption often point to denser, dustier, or more shielded environments. In other words, different BAL types reveal different layers and conditions inside quasar outflows. High BAL quasars are the most common BAL type. They usually show high ionization outflows, and they may represent lines of sight that cut through a wind launched from the accretion disk, but not through the densest or dustiest parts of the system. Low BAL quasars are less common and often redder, which suggests more dust along the line of sight. Fellow-Bal quasars are rarer still, and are often especially dusty and complex. Some astronomers have suggested that low-Bal and Philo-Bal quasars may represent young or transitional phases, perhaps when a quasar is still emerging from a dust-rich environment and blowing material away. But orientation may also play a role. As usual, the universe has not chosen between geometry and evolution in a way that makes life easy. It may be using both. The idea of orientation is central to BAL quasars. If the wind covers only part of the sky, as seen from the central black hole, then only observers whose line of sight passes through the wind will see BAL features. Observers looking from another angle may see the same basic quasar without broad absorption troughs. In this view, BAL quasars are not necessarily a completely separate kind of quasar. They may be ordinary quasars viewed through an outflow. This is similar to the way broad line and narrow line classifications depend partly on whether dust blocks the inner regions. The same engine can look different depending on whether our line of sight crosses gas dust, a jet, or a relatively open path. Yet orientation may not be the whole story. BAL quasars, especially low-Bals and Fellow-Bals, often show signs of dust reddening and unusual environments. That suggests that some BAL quasars may also represent stages in quasar evolution. A growing black hole may be surrounded by gas and dust during a powerful feeding phase. As radiation pressure and winds strengthen, the quasar begins to blow away its cocoon. During that phase, the line of sight may pass through dense outflowing material, producing BAL features. Later, after the material has been cleared, the quasar may appear bluer and less absorbed. This evolutionary picture is appealing because BAL winds look exactly like the sort of thing a quasar might use to clear its surroundings. Still, it probably does not explain every BAL quasar. Nature often uses one phenomenon for several jobs, which is efficient if slightly inconvenient for classification. The wind has to be launched somehow. Radiation pressure is one likely part of the answer. The accretion disk around a quasar emits an enormous amount of light, especially in ultraviolet wavelengths. Photons carry momentum. When they're absorbed or scattered by gas, they can push on it. In line-driven wind models, radiation pushes most effectively through absorption in spectral lines. This is similar in spirit to how winds are driven from hot massive stars, though the quasar environment is much more extreme. Gas lifted from the disk can be accelerated outward by the quasar's intense radiation. Magnetic forces may also help launch or guide the flow. The real wind may involve radiation, magnetism, shielding gas, disk structure, and geometry all working together in a complicated arrangement. Shielding is important because the wind must not become too ionized. If the gas is blasted by too many X-rays, its electrons can be stripped away so completely that it no longer has the right ions to absorb ultraviolet line radiation effectively. In that case, radiation pressure through lines becomes weaker. Some models include a shielding region that protects the wind from excessive X-rays, while still allowing ultraviolet light to accelerate it. This is a delicate balance. The quasar must be bright enough to push the gas, but not so harsh in the wrong way that it removes the wind's ability to catch the light. Even cosmic winds need a little shade. This makes BAL quasars very useful laboratories for understanding accretion disk winds. The absorption troughs tell us that gas lies along our line of sight. The depth of a trough tells us about how much light is blocked, though interpreting that can be tricky because the wind may cover only part of the source. The width tells us about the range of velocities. The shift tells us the overall speed away from the quasar. The presence of different ions tells us about ionization and density. Changes over time tell us whether clouds are moving across our view or whether the ionization state is changing as the quasar brightens and fades. A BAL spectrum is not just a category, it is a moving diagnostic. Variability is especially valuable. BAL troughs can change over months or years in the quasar's rest frame. Sometimes an absorption feature grows deeper, sometimes it weakens, Sometimes parts of the trough change while other parts remain steady. This can happen because clouds in the wind move across the line of sight, covering more or less of the bright source. It can also happen because the ionizing radiation changes, altering the state of the gas. Distinguishing between these explanations is difficult, but both are informative. If clouds cross the line of sight, their motion gives clues to wind size and location. If ionization changes, the response tells us about density and radiation. The wind changes and the changes help map it. The location of BAL gas is one of the great questions. Some outflowing material may lie very close to the accretion disk, perhaps at subparsec or parsec scales. Other components may be much farther out, tens, hundreds, or even thousands of parsecs from the central engine. Different observations may trace different parts of the outflow. Ultraviolet, BALs, may come from one region. X-ray absorption may come from another. Molecular outflows on galactic scales may represent a later, larger response to the quasar's energy. The word wind can therefore describe several linked zones, from the inner disk atmosphere to galaxy-wide gas pushed outward by accumulated energy. A famous BAL quasar example is APM 08279 plus 5255. It is a very distant, gravitationally lensed broad absorption line quasar at high redshift, and its lensing makes it appear brighter than it otherwise would. That natural magnification has allowed astronomers to study it in unusual detail. APM 08279 plus 5255 is especially interesting because it has shown powerful absorption associated with high-speed material, including studies of X-ray broad absorption features. It is also known for enormous amounts of gas and dust, and for being one of the most luminous quasar systems studied. It is the kind of object that makes catalogue names feel too small. A PMO 8279 plus 5255 sounds like a filing label, but behind it is a lensed, distant, hyperluminous black hole system with winds, dust, and ancient light all tangled together. Another important example is MRK 231, also known as Markarian 231. It is much closer than most quasars and is often described as the nearest quasar. It is also an ultra-luminous infrared galaxy and a merger remnant with powerful outflows. MRK 231 hosts a nuclear ion low ionization broad absorption line outflow, making it a key nearby example for studying dusty BAL behavior and feedback. Because it's comparatively close, astronomers can study details that would be much harder to see in distant quasars. It gives us a local laboratory for the kind of wind-dominated activity that may have been more common in the younger universe. In MRK 231, the quasar, starburst, dust and outflow are all part of one messy energetic system. The black hole is not acting alone. The galaxy around it is actively involved. MRK 231 is also a useful reminder that BAL quasars can be deeply connected with galactic-scale winds. The central BAL outflow may be part of a larger feedback process in which the active nucleus helps drive gas out of the galaxy, or disturb the star-forming material. This is one of the reasons BAL quasars are more than spectral oddities. They may be showing us quasar feedback in action. The absorption troughs are not merely dark marks on a graph. They may be the small-scale signature of energy leaving the black hole environment and eventually changing the host galaxy's ability to form stars. Feedback is one of the big themes in modern galaxy evolution. Galaxies grow by collecting gas and turning some of it into stars. Supermassive black holes grow by accreting gas in the centers of galaxies. But if gas simply cooled and collapsed freely in massive galaxies, many galaxies might form too many stars compared with what we observe. Energy from active galactic nuclei can help regulate this. Jets can heat surrounding gas, radiation can push on dust, winds can carry mass and energy outward. BAL quasars are one of the clearest signs that quasars can launch winds from their central regions. Whether each wind has enough power to reshape the entire galaxy depends on its mass, speed, covering factor, and duration. But the potential is there, written in the absorption. The absorption troughs can be so wide that they seem almost like gaps carved into the spectrum. To astronomers, those gaps are rich with information. The edge of a trough can reveal the maximum velocity of the wind. The depth can suggest how much of the continuum source is covered, although saturation can make this difficult. A line can be saturated, meaning the absorbing gas is already removing nearly all the light at that wavelength along the covered path, but the trough may not go black if the wind only partially covers the source, or if some light is scattered around it. So a shallow trough does not always mean little gas. It may mean complex coverage. The quasar is not a simple lamp behind a simple screen. It is a bright, structured source behind a clumpy, moving absorber. This partial covering idea is important because the emitting regions of a quasar have different sizes. The ultraviolet continuum source is compact. The broadline region is larger. The dusty infrared emitting region is larger still. A wind cloud can cover one region more than another. It may block part of the disk, but not all of the broadline region. It may absorb some emission lines differently from the continuum. This can make BAL spectra hard to interpret, but also more useful. The complexity tells us about the relative sizes and geometry of the components. A messy absorption feature may be frustrating, but it is not meaningless. It is the wind drawing a rough map of the source behind it. BAL quasars are often X-ray weak compared with ordinary quasars. In many cases, this is because absorbing gas blocks or reduces the X-ray light along our line of sight. The X-ray absorber may be connected to the same wind or to shielding material that protects the ultraviolet wind from over-ionization. Some BAL quasars may also be intrinsically X-ray weak, meaning the central engine produces fewer X-rays relative to its optical and ultraviolet output. This distinction matters because X-rays strongly affect the ionization of gas. If too many X-rays escape into the wind, they can strip the gas too thoroughly. A weaker or shielded X-ray source may help the BAL wind survive. Once again, absence becomes a clue. Less X-ray light may help explain more ultraviolet absorption. There is a quiet elegance in that. The quasar must make enough light to drive the wind, but not too much destructive high-energy light in the wrong place. The gas must be ionized enough to absorb in the right lines, but not so ionized that the relevant ions vanish. The wind must be dense enough to leave strong troughs, but not so thick in every direction that the quasar disappears completely. It is a balance of radiation, gas, dust, magnetism, and angle. BAL quasars occupy that balance in a way that lets us see it. Fellow BAL quasars are especially intriguing because they often look dusty, red, and heavily absorbed. The ion absorption lines can come from complex, dense gas, and these objects are rare. Some fellow BALs may represent quasars in a brief transitional phase, perhaps when the central engine is blowing through a dusty cocoon left by a merger or intense starburst. If that is true, they may be snapshots of quasars clearing their surroundings, but because they are rare and complicated, it is hard to know how universal that story is. Some may be mainly orientation effects, seen through a particularly thick part of the wind. Others may genuinely be young or transitional. The debate itself is useful, because it reminds us that a category can contain multiple physical histories. Low BAL quasars sit between the more common high BALs and the rarer fellow BALs. They show low ionization absorption and are often redder than typical quasars. That redness suggests dust, and dust suggests either a particular viewing path or an evolutionary stage rich in gas and dust. Low BALs may have stronger connections to infrared luminous systems, mergers, or heavily obscured growth phases, though not every low BAL must fit the same picture. Like so many quasar types, they are not a single note, but a chord. The relationship between BAL quasars and radio loudness is also interesting. Many BAL quasars are radio quiet, but radio loud BAL quasars do exist. This complicates older ideas that BAL whines only appear in certain simple geometries. If a quasar has both radio structure and BAL absorption, astronomers can use the radio information to estimate orientation and compare it with the wind signatures. Some radio BAL quasars suggest that BAL outflows can be seen over a range of viewing angles, not only one narrow equatorial band. The wind may be clumpy, patchy, or structured in ways that allow absorption from different directions. Once again, the universe refuses to be a flat diagram. The velocities of BAL winds are among their most striking features. Many reach thousands to tens of thousands of kilometers per second. Some extreme outflows reach a significant fraction of light speed. These are not winds like anything on Earth. They're not driven by warm and cold air balancing pressure in an atmosphere. They are driven by radiation, magnetic forces, and the extreme conditions near an accreting black hole. Calling them winds is useful, but it is also a little misleading. A terrestrial wind can move leaves. A quasar wind can carry enough energy to influence a galaxy. The same word is doing very different jobs. Still, the word wind has a calming simplicity, and perhaps that is why it helps. Wind is moving material. It has a direction. It carries energy. It can reshape its surroundings over time. On Earth, wind carves dunes, bends trees, carries seeds, and slowly changes landscapes. Around a quasar, the wind may carve spectral troughs, push gas from the nucleus, carry metals into the host galaxy, and help regulate star formation. The scales and physics are different, but the idea of a flow reshaping a place remains. BAL quasars also show that quasars are not only about what falls in, they are about what comes out. It is easy to focus on accretion, because the black hole feeding process powers the light. Matter spirals inward, energy is released, the central engine shines, but the outward side is just as important. Jets carry energy along narrow channels. Radiation streams outward in all directions that are not blocked. Winds lift gas from the disk and drive it into the surroundings. The quasar is an exchange, not a one-way drain. Matter goes in. Energy and sometimes matter come out. The galaxy feels the consequences. If you imagine the central region of a BAL quasar, it might look something like this. At the center, the black hole remains invisible. Around it, the accretion disk glows intensely, brightest in ultraviolet light. Above the disk, or rising from it at an angle, a wind of ionized gas is being launched. Some gas is shielded from too many X-rays, allowing line pressure to accelerate it. The wind is not smooth. It is clumpy, structured, perhaps filamentary. It crosses our line of sight to the bright disk. As the disk light passes through, specific wavelengths are absorbed by carbon, silicon, magnesium, iron, or other ions. The light continues toward Earth with dark troughs pressed into it. Billions of years later, a telescope records those troughs, and astronomers recognize the mark of a quasar wind. That picture contains both violence and patience. Near the black hole, everything is fast, hot, and bright. The gas is racing outward. The radiation is intense. The environment is hostile beyond imagination. But the message travels quietly. A photon that survives the wind enters the expanding universe. It crosses intergalactic space. Its wavelength stretches. It passes through clouds, voids, and the outskirts of galaxies. Eventually it arrives at a mirror, a detector, a line in a spectrum. The wind that once moved near a black hole becomes a dark shape on a graph. That is how gentle astronomy can be, even when the places it studies are not gentle at all. BAL quasars bring many earlier ideas together. They involve the bright disk of ordinary quasars. They depend on line-of-sight effects like narrow line and obscured quasars. They can be reddened by dust like red quasars. They may vary like changing look and other active systems. They can coexist with radio properties, though they are not defined by jets. Most of all, they show that quasar engines do not simply shine. They can drive matter outward, and that outward motion may connect the small black hole environment to the large life of a galaxy. The The broad absorption trough is therefore one of the most meaningful shadows in astronomy. It is not darkness caused by absence alone. It is darkness caused by moving material. It tells us that somewhere near the edge of a quasar's brightest region, gas is escaping, carrying mass, momentum and energy away from the black hole. It tells us that a galaxy's blazing heart can blow as well as burn. It tells us that the light from a quasar has crossed a wind before crossing the universe. And so we have come, slowly and carefully, to the wider view. Not just one quasar now, not just one bright point at the edge of a telescope image, but a whole family of cosmic engines, each one showing us a different face of the same deep process. A supermassive black hole sits in the centre of a galaxy. Matter falls toward it. The matter cannot fall neatly, because it has motion, spin, heat, and pressure of its own. So it gathers into a disk, circles inward, grows hotter, shines fiercely, and turns gravity into light. Around that centre, gas moves, dust hides, magnetic fields twist, winds rise, and sometimes jets leap outward across distances so large that the host galaxy begins to look almost small beside its own consequences. That is the quasar story in its simplest form, though as we have seen, the simple form is only the doorway. At the beginning of our journey, quasars may have seemed like one kind of object, a bright galactic centre, powered by a feeding black hole, visible from very far away. And that is true. But truth in astronomy often begins simple and then grows branches. A quasar is not only a bright thing, it is a system seen from an angle, through a medium, at a certain stage of activity, in a certain cosmic era. Change the angle, and a jet may dominate. Add dust, and the quasar may redden or hide its broad lines. Look down the jet and the object becomes a blazar, flickering with beamed light. Let a wind cross the line of sight, and the spectrum grows dark troughs, becoming a broad absorption line quasar. Watch long enough, and in some cases the quasar seems to change its look entirely, as the central engine brightens or fades, and the gas around it responds. This is one of the main lessons every quasar type teaches us. Classification is useful, but nature is not built out of perfect labels. Radio loud, radio quiet, broad line, narrow line, red, blue, changing look, blazar, OVVBAL. These names help astronomers organise what they see, but each name is also a hint about physics. Radio loud tells us about powerful jets and strong radio emission. Radio quiet tells us that giant jets are weak or absent, while the accretion disk and winds may still be enormously powerful. Broad line tells us fast gas near the black hole is visible. Narrow line tells us the inner region may be hidden behind dust, leaving only slower gas farther out to speak clearly. Red and blue tell us about dust, temperature, and the path light has taken. Changing look tells us that some quasar engines can shift states on timescales, short enough for human observers to notice. Blazars tell us about relativistic beaming. BAL quasars tell us about winds leaving the disk and carving shadows into light. In other words, every type is a clue, not a separate universe. The black hole itself remains the quietest part of the whole arrangement. That may sound strange because we spend so much time talking about black holes as monsters, engines, and cosmic power sources. But the event horizon does not shine. It does not send us a photograph of its interior. The light we study comes from outside it, from matter not yet lost, from gas still struggling, orbiting, heating, escaping, or being pushed away. The quasar is the bright edge of darkness, not the darkness itself. It is what happens when the deepest gravitational wells in galaxies are surrounded by fuel. A black hole with nothing nearby can sit almost invisibly. A black hole with a rich supply of gas can become one of the most luminous objects in the observable universe. The difference is not just the hole, the difference is the meal. That is why quasars reveal so much about black hole growth. They show us black holes during active feeding phases. Our own galaxy's central black hole, Sagittarius A star, is mostly quiet today. It gives off radiation, and it occasionally flares, but it is not a quasar. It is not surrounded by enough infalling material to outshine the Milky Way. Yet in the past, many galaxies seem to have gone through far more active phases. Their central black holes grew, perhaps during mergers, perhaps during gas-rich periods, perhaps during long episodes when material found its way inward from larger galactic scales. A quasar is a sign that the central black hole is not merely present, it is growing, or at least being supplied with enough fuel to shine as though it is. This growth creates a question that still troubles astronomers in the best possible way. How did the earlier supermassive black holes become so massive so soon? Some quasars are seen from when the universe was very young. Their light has crossed more than 13 billion years to reach us, and yet the black holes powering them can already contain hundreds of millions or even billions of solar masses. That is difficult to explain with slow, ordinary growth from small black hole seeds. Maybe some seeds were born large, from direct collapse of huge gas clouds. Maybe some black holes fed extremely rapidly. Maybe mergers helped. Maybe the first galaxies provided special conditions we are still learning to understand. Early quasars are not just distant lamps. They're questions glowing from the dawn of cosmic structure. Every quasar type helps with that problem in a different way. Blue, unobscured quasars let us measure broad emission lines and estimate black hole masses. Dusty red quasars may show growth phases hidden from optical surveys. Radio-loud quasars and blazars reveal the early presence of jets and magnetic engines. BAL quasars show winds that may regulate black hole feeding and galaxy growth. Changing-look quasars show that accretion can vary dramatically, reminding us that black hole feeding may not be smooth. Together they tell us that growing a supermassive black hole is not one simple process. It is a complicated exchange between gravity, gas supply, radiation, magnetic fields, dust, and time. Quasars also reveal that galaxies and black holes are connected more deeply than they first appear. A black hole may be tiny compared with its galaxy. Even a supermassive black hole's event horizon is small beside the galaxy's disk, bulge, and halo. It is like comparing a seed to a forest, and yet the energy released near that black hole can influence gas across enormous distances. Jets can heat surrounding material. Winds can push gas outward. Radiation can ionize clouds and affect whether gas cools. Dust can absorb the energy and glow in infrared light. A quasar phase can therefore shape the galaxy that hosts it. The small center can help regulate the large home. This is part of the idea of feedback. The word sounds plain, almost too ordinary for what it means. It is not feedback like a microphone squeal, though if a quasar could make a sound in air, one suspects it would be asked to leave the room. In galaxy evolution, feedback means that energy from stars or active black holes changes the gas around them. That gas is the raw material for future stars. If it cools and collapses, stars may form. If it is heated, stirred, or pushed away, star formation can slow. Quasars may help explain why some massive galaxies stopped forming stars as actively as they once did. They may also help distribute heavy elements through galactic and intergalactic space. The black hole feeds, but it also answers back. The different quasar types are therefore not just visual categories, they are different forms of feedback and visibility. A radio-loud quasar shows feedback through narrow, powerful jets that can inflate lobes far beyond the galaxy. A radio-quiet quasar may show feedback through radiation and broad winds instead of enormous radio structures. A BAL quasar gives us direct evidence of outflowing gas in the line of sight. A red quasar may show us a dusty stage when the black hole is still wrapped in material. A narrow-line quasar may reveal a hidden engine through the gas it illuminates outside the obscuring dust. A blazar shows us what happens when a jet is aimed almost directly toward us, boosting the signal and letting us study extreme particle acceleration. Each type is a window into how energy escapes from the center. They also teach us humility about perspective. We often speak as if the universe has fixed categories, but many quasar differences depend on our viewing angle. If our line of sight looks into the central region, we may see broad lines. If dust blocks that path, we may see only narrow lines. If a jet points sideways, it may appear as extended radio structure. If it points nearly toward us, it may become a blazar. If a disk wind crosses the bright source, we may see BAL troughs. The object has its own structure, but our view selects part of it. Astronomy is full of this lesson. What something is and how something appears are related, but they are not identical. That is not a weakness in astronomy. It is part of the work. Astronomers cannot fly around a quasar and choose a better angle. They cannot move a dusty torus aside with a cosmic feather duster, though that would be very convenient. They collect light from where Earth happens to be, then compare many objects seen from many natural angles. Over time, a three-dimensional picture emerges from thousands of one-dimensional lines of sight. It is like trying to understand a sculpture by looking at shadows cast on different walls. No single shadow is the whole sculpture, but many shadows, carefully studied, begin to reveal the shape. Quasars also teach us that light is a traveller. The light from distant quasars does not simply leave the accretion disk and arrive unchanged. It may pass through a wind, losing certain wavelengths to absorption. It may pass through dust, becoming redder. It may be scattered by gas. It may be stretched by cosmic expansion. It may pass through clouds of hydrogen between galaxies, leaving marks that tell us about the intergalactic medium. It may be bent and magnified by gravitational lensing. By the time it reaches a telescope, the light has become a layered document. Some parts describe the black hole, some describe the host galaxy, some describe the space between galaxies, some describe the expansion of the universe itself. That is one reason quasars are such powerful tools for studying the early universe. They are bright background beacons. Their light can shine through intervening gas and reveal what that gas was like at different cosmic times. In very distant quasars, absorption by neutral hydrogen helps astronomers study the epoch of reionization, the era when the first stars, galaxies and black holes helped transform the universe from a fog of neutral gas into the more transparent cosmos we see today. The quasar is interesting in itself, but its light also illuminates the road it took. A single, distant quasar can act like a lighthouse, a timestamp, a probe, and a puzzle all at once. There is something quietly moving about that. A quasar may be powered by one of the most extreme environments nature can build, yet from Earth it arrives as information. A point on a detector, a line in a spectrum, a colour in a survey, a flicker in a light curve, a radio map with lobes, an X-ray absorption feature. A gamma-ray flare. The violence is translated into measurement. The black hole's surroundings become numbers, wavelengths, delays, widths and shifts, and from those delicate things, we learn about galaxies billions of light years away. The story also changes how we think about black holes. In popular imagination, black holes often appear as endings, places where matter disappears and stories stop. Quasars show a different side. Near a feeding black hole, before matter crosses the event horizon, the universe can become extraordinarily bright. The black hole is not simply a drain. It is part of an energy system. It can turn in falling matter into radiation with tremendous efficiency. It can help launch jets. It can drive winds. It can shape galaxies. The darkness at the centre does not prevent light. In the right conditions, it helps create one of the brightest phenomena in the universe just outside itself. That is a strange and useful correction. Black holes are not only cosmic endings, sometimes around them, galaxies blaze. Quasars also make us think about time in a larger way. Many of the quasars we study are not shown to us as they are now, but as they were when their light began its journey. A quasar seen 10 billion light-years away is not a live broadcast in the ordinary sense. It is ancient light reaching us now. The object may have changed, faded, merged, or gone quiet long ago from its own later history. But its earlier light is still arriving. This means the sky is not only a map of space, it is a map of time. Quasars are among the brightest markers on that time map, showing us eras when the universe was younger, denser, and more active in building galaxies and black holes. For a sleepy mind, that thought can be held gently. Somewhere, long before Earth had complex life, a supermassive black hole in a young galaxy was feeding. Its disk shone, its gas emitted broad lines, perhaps its dust reddened the light. Perhaps it launched a jet, perhaps a wind carved absorption troughs into its spectrum. The light left, crossed expanding space, and kept going. While it travelled, stars were born and died, galaxies merged, the Milky Way changed, the sun formed, Earth cooled, oceans gathered, life began, struggled, diversified, and eventually produced beings who built telescopes. Then a few photons from that ancient quasar arrived and were caught, a message sent by no mind, understood by one. That is the calm wonder behind quasar astronomy. It does not require the universe to be kind or purposeful. It only requires that light carries information and that patient observers learn how to read it. The quasar does not know we are here. The black hole does not know it has become a subject for bedtime narration. The jet does not aim at us with intention. The wind does not carve its absorption line for our benefit. And yet, through physics, all of it becomes readable. The universe is not explaining itself in words, but it is not silent. Each quasar type gives us one sentence in that larger explanation. Radio-loud quasars say that black holes can send energy into long jets. Radio-quiet quasars say that enormous power can hide without giant radio beams. Broadline quasars say that fast gas near the black hole can help us weigh the unseen centre. Narrow-line quasars say that dust can block the direct view while the outer gas still glows. Red quasars say that colour can reveal dust, environment, and perhaps stages of emergence. Blue quasars say that a clearer view of the hot disk can shine across the cosmos. Changing-look quasars say that the engine is not always steady, and that even enormous systems can shift on human timescales. Blazars and OVV quasars say that speed and angle can make light appear brighter, faster, and more restless. BAL quasars say that quasars can blow winds strong enough to mark their own spectra, and perhaps reshape their galaxies. Taken together, they reveal a universe that is active, connected, and still not fully understood. The early universe built black holes faster than we can easily explain. Galaxies and black holes grew together in ways we are still untangling. Jets and winds carried energy outward. Dust hid some of the growth. Light from the most distant quasars continues to help us measure the matter between galaxies and the history of cosmic expansion. Each answer opens another question. That is not a failure of science. It is the reason science keeps moving. And here, near the end of our long drift through quasar types, it is worth returning to your own quiet place for a moment. You may be listening in a dark room, or under a blanket, or beside a window where the sky outside is cloudy, bright with city lights, or scattered with a few patient stars. Maybe it is late where you are. Maybe it is morning. Maybe time has softened a little while we have been moving through black holes, dust jets, winds, and ancient light. So let me ask you again, gently. Where are you listening from, and what time is it in your little part of the world? It is a fitting question, because quasars remind us that time is not just what clocks measure. Time is also distance. Time is light crossing space. Time is a galaxy seen as it was when the universe was young. Time is a black hole feeding billions of years ago, while its signal arrives tonight, quietly, at the edge of your attention. The quasar may be violent in its own place, but here it becomes a story, a soft chain of ideas, a way to let the mind travel far without needing to leave the room. If this journey through the brightest engines in the universe brought you a little calm, a little curiosity, or simply a pleasant place to rest your thoughts, I would be grateful if you liked the video, subscribed, or shared it with someone who might enjoy falling asleep beside a supermassive black hole in the safest possible way. That is one of the nice things about astronomy from Earth. We can visit extreme places by thought and light alone, with no need for a heat shield, a radiation suit, or a very brave insurance policy. So now, let the quasars recede a little. Let the radio jets stretch away into the dark. Let the dusty Tori settle back around their hidden centres. Let the broad lines, narrow lines, red colours, blue colours, changing looks, beamed flares, and absorption troughs become part of one larger picture. Across the universe, black holes are not merely dark holes in space. In the right galaxies, at the right times, with enough gas falling inward, they become engines of light and motion. They help reveal how galaxies grew, how matter moved, how the early universe changed, and how even darkness can be surrounded by brilliance. And somewhere far beyond the Milky Way, beyond the stars you can see, beyond the quiet edge of ordinary night, old quasar light is still travelling. Some of it left its galaxy before Earth existed. Some of it began its journey when the universe was young and crowded with unfinished structures. Some of it is arriving now, touching mirrors, entering detectors, becoming spectra, becoming knowledge. It has crossed almost everything to reach us, and it asks for nothing except to be read. Sleep well, fellow traveller, wherever and whenever you are. The universe is still shining in the distance, still changing behind the dark, still sending its ancient messages through space. And for now, here in this small calm moment, we can let those messages drift on without chasing them any farther tonight.